Sir, webinar has been started, sir.
So, sir, that we can start at 9:15. Okay.
Okay, sir.
And by 10 o'clock, this
First-
session will be
Yeah,
completed.
first, who is the first?
Sir, Professor Subrato Bhattacharya is already joined.
Okay.
You are having now, sir, schedule?
Yeah. No, I don't have the.
Actually, again, I am sending the schedule to you.
No problem, sir. First is Professor Bhattacharya, about 50 minutes. Okay. Next, sir, just tell.
Then Professor Abhinav Kumar Agarwal
Okay.
is to 10 to 10:30, and Professor Swarit Kumar Das 10:30 to 11,
Okay.
and Professor Pradeep Chaturvedi 11 to 11:15.
Okay.
Huh, sir?
Right,
Like
sir.
this way, we have to go ahead.
No problem, sir. No problem.
So you maintain the timing.
Joel, numbers.
গৌতম ওই চেয়ারম্যান টিএসসি নামের আগে নামটা দিয়ে দে, ইঞ্জিনিয়ার চিন্ময় দেবনাথ সি দেবনাথ নামটা দিয়ে দে। ওই যে দেখ কারসারটা যদি ইয়েতে নিস, ছবিটার মধ্যে ডান দিকের কোণার মধ্যে 3টে ডট আসে, ওখানে গিয়ে ক্লিক দেখবি যে রিনেম আসে। চিন্ময়দা, সুব্রতদাকে তো চিনোই তুমি।
হ্যাঁ, গুড মর্নিং সুব্রতদা।
Good morning. অনেকদিন
Can you
পরে
recognize me?
Yes,
Can you recognize me?
You're very familiar. Yep. I think I have seen you.
79 batch, ধ্রুবনারায়ণ দত্ত।
Dhruv batch, exactly. Dhruv তো এখন বোম্বে না?
তোমরা নেক্সট ব্যাচ।
আচ্ছা।
ধ্রুব বোম্বেতে আছে।
বোম্বেতে আছে, রাইট। কথা হয়েছিল একবার। তুমি তো এনআইটি তে আছো?
না, আমি তো পিডব্লিউ থেকে রিটায়ারমেন্টে গেলাম লাস্ট ফেব্রুয়ারি।
আচ্ছা। এত তাড়াতাড়ি রিটায়ারমেন্ট?
না, রিটায়ারমেন্ট ফ্রম গভর্নমেন্ট সার্ভিস, বাট নট ফ্রম দ্য জব।
Not from profession. Good.
Right from morning to evening, engage in some other job. Obviously, voluntary service.
Of course. Thank you. And where is Professor Srivastava joining from? Are you joining from NIT or?
Yeah.
I'm from Nagpur, sir.
Oh, really? Okay. Please call me Subroto. Please, everybody call me Subroto. I love that.
Sir.
Good morning, Srivastavaji.
Good morning, Chinmay sir. Good morning.
One information, Subroto.
Yes.
Today, you and Srivastavaji both are connected with me. Actually, I admitted in REC Nagpur in the same batch of Srivastavaji.
Oh.
In 79.
Oh, nice.
Then after 1 month, I came back to Tripura Engineering College after getting civil engineering division, the branch. So 1 month we were best mate there.
Oh, very nice. Excellent. So how did you guys organize this meeting in Agartala? Because this is national meeting, right? So the Agartala committee, Shaban Babu took over or something?
No, actually, what is happened that we have to send the proposal in our national council May. So in the national council approved this one 4 years before. it's supposed to held last year, but due to the COVID situation, it was not there. So this year, actually, again, COVID and others, whether we'll be doing a physical mode or the virtual mode, under this situation, it is delayed. So now we are organizing into the virtual mode completely for our technical sessions, and the only inaugural and valedictory session will be in the dual mode, physical and virtual. In our institution of engineers building, we have inaugural session has been organized both way, and now also in the valedictory session it will also be organized in both way, that is the physical and virtual. So Srivastava,
So,
if people will be joining, we'll start our business. Huh?
yeah.
Now 9:15 will be there because he has to complete by 10 o'clock. So,
Homi Babu, Abhijit Bhattacharya from Hyderabad, no, Sumitra Bhattacharya from Hyderabad saying no sound, or from Abhijit Bhattacharya. I think there is sound. If you open the chat, you can see.
Sure. You want.
Maybe
they are. Oh, okay.
Maybe he's having some problem with his own computer. Everyone seems to be okay.
Abhijit Bhattacharya, please, when you have joined, you have to wait something that wait for a while that Zoom will ask you that you will be joining with the laptop sound or your any other mode. So you can give the laptop sound, then only you can hear. So you can go out and join again. Sir, so, Chairman sir, we are going to start. Okay. So good morning to all. Today, this is the second day of the 36th National Convention of Mechanical Engineers and National Seminar on Innovations in Thermal Science and Engineering, being organized by the Tripura State Center of the Institution of Engineers India under the aegis of Mechanical Engineering Division Board of the Institution of Engineers India. Today it is our 5th session, technical session, and yesterday there was a inaugural session, then 3 technical sessions we have concluded, and we have made our effort to have all the renowned personalities on this thermal sciences. And yesterday our second session was they are from the 4 countries, starting from Australia, Japan, Singapore, and India. And today we are having from our US as well as India. And today's it was starting with our Professor Subrata Bhattacharya, who is from the Samdeogi University, and our Professor Avinash Kumar Agarwal from IIT Kanpur, Professor Shorit Kumar Das from IIT Madras, and Engineer Pradeep Chaturvedi of Delhi. And before starting our program, I welcome our session chair, Professor Rakesh L. Srivastava. He was and our co-chair, Professor Dr. Bipin Kumar Tripathi, and our rapporteur, Dr. Rahul Banerjee and Dr. Madhujit Dev. So before starting the session, I should introduce our session chair and co-chair very shortly. Dr. R.L. Srivastava is a former professor of mechanical engineering. He is having more than 38 years of teaching, training, consultancy, research, and industrial and administrative experience. He has had his education and training in mechanical and production engineering at Bachelor of Engineering, MTech, and PhD level. He is a MBA as well. He is also a certified master black belt in Lean Six Sigma and a qualified lead assessor for ISO 9001 QMS and ISO 50001 ENMS. He is an examiner for IMC Ramakrishna Bajaj National Quality Award. Professor Dr. Srivastava has guided several organizations on quality and productivity improvement and organizational excellence. He has contributed to 50 plus papers at national and international level at various journals, seminars, conferences. He is a reviewer for international journals and publications houses such as TQM, JCLP, SME, Taylor Francis, IEEE, Elsevier, Emerald, Science, etc. He has produced 19 PhDs and 4 scholars have already submitted, and so many scholars are working under him. He is the recipient of several honors and awards and has been an expert in developing systems that are efficient, effective, productive, quality focused, and lead to excellence in performance. He has won several best paper awards, worked on many committees, written books, and examined a number of MTech PhD theses. He is associated with the Institution of Engineers India as well as Indian Institution of Industrial Engineering, and also renders his service as a chartered engineer. He has completed many assignments of valuation of machineries and accessories, both old and new, for customs and other bodies. Presently, he is the chairman, the Institution of Engineers India, Nagpur Local Center, a National Council member of the Institute of Engineers India, Kolkata. With this brief introduction, I will be handing over to the microphone to the Srivastava. Before handing over, I should also introduce our co-chair, Professor Dr. Bipin Kumar Tripathi. He is a professor for Mechanical Engineering Department of NIT Agartala. Before joining at NIT Agartala, he was the faculty member of College of Engineering, Pune. So welcome, Bipin Tripathi ji. As well as our rapporteur, Dr. Rahul Banerjee. He is the assistant professor, Mechanical Engineering Department, NIT Agartala. As well as Dr. Madhujit Dev, the assistant professor, Mechanical Engineering Department, NIT Agartala. So now over to Professor Srivastava for conducting the rest sessions. Please.
Thank you, Professor Swapan, for a wonderful introduction and beginning of technical session 5th, number 5 of this National Convention of Mechanical Engineers. Respected Chinmay sir, co-chair Professor Vipin, and the reporters, the first talk today that we have is to be delivered by a very distinguished Professor Subrata Bhattacharjee, and I'm very pleased to introduce Professor Subrata, who is well known to his friends as Subi. Right? He earned a BTech degree in mechanical engineering from IIT Kharagpur in 1983 and earned his PhD from Washington State University, USA in the year 1988. After 2 years of postdoctoral work on a NASA project, he joined San Diego State University in 1991 and currently holds professorship in Mechanical Engineering Department and adjunct professorship in Computer Science Department. Professor Subrata has been actively involved in research in radiation heat transfer, combustion, computational thermodynamics, and development of software for educational purposes. For his dissertation, he developed a modified two-flux method, that is effective angle method, for calculating radiation source term, and used this model to study two-way coupling between radiation and fluid dynamics in a laminar diffusion flame. Working on a project on jet flow in boundary layers, he came upon a non-dimensional group that compares a known pressure drop with viscous forces. This number is being used in textbook and literature in connection with electronic cooling. Winner of Outstanding Faculty Award, Monty Award, Most Influential Faculty Award, Faculty Friend Award, Outstanding Engineer Educator Award, Best Paper Award, and ASME Fellow Award. So a wonderful distinguished professor we have this morning with us, and I take pleasure in inviting Professor Subi.
Before starting the Professor Subi, I must tell one thing, that he belongs to, he's hailed from Tripura, and he obtained his, he was a first rank holder in the Madhyamik as well as class 12 from the Tripura Board of Secondary Education. And everybody, he is inspiring each and everybody, and so many people are inspired by him. And now over to Subrata, please.
Oh, thank you. Thank you, Professor Srivastava and Professor Bhaumik. By the way, how much time I have? I have to finish in
about 40 minutes.
About 40 minutes.
By 10 o'clock.
By 10 o'clock.
Okay, got it. Thank you.
Indian time.
Okay. Thank you so much for the kind introduction. It's my pleasure to really talk today. So I will first share my, just give me a second, website with you. Okay, I hope you can see, this is the program, and I will basically go between tabs here. These are my slides, and I have the chat open. No, I cannot. Okay, I'm sharing. Just if you want to pause or have a question, just please let me know. So I will start with some acknowledgement. Pearson has been very generous to me. They have supported my work in this particular venture of developing the expert system. And throughout my career, I have been supported by NASA. I've been very lucky. My latest funding is from for another $500,000 for next 5 years. And government of Japan has supported me at various times. And of course, Professor Bhaumik for inviting me to join my hometown people to present a paper, present some thermodynamic talk to the general Indian engineers. So I'm so proud to be from Tripura and presenting on behalf of the Engineers India Institute. Hopefully next year we can meet in person. One good news, after almost 2 years, my first in-person conference was a couple of weeks ago, and it went fabulously. Of course, it was before Omicron came to be well known. Okay, the overview of the talk would be, I'll be presenting slide like this and going back and forth so that we can do some hands-on examples of what this is all about. And I'll primarily talk about the calculators called test apps, online apps that can be used to solve almost all kinds of thermodynamic problems. So first, let me start with how do you access test. And by the way, anyone who is attending today's talk, if you create an account, just let me know and I'll make your account permanent if you like this particular application. So currently there are a lot of educators, engineers, and students who are kind of registered for this website, and it's constantly used all over the world. That's one of the nice things to see when something you do is being used. So I'll not spend much time on the scope of what it does. These are, I intentionally wrote on the slides. And by the way, these slides also will be accessible from the portal. I already put them on the website. So it's under the publications category. So let me just first tell you where you can find it. This is the site, thermofluids.net, and the publication is linked here. And if you go down the publication list, at the very bottom, you will see today's talk. So these slides that I'm showing are available for everyone. So now, something more about publication. There are a couple of textbooks that has been published that kind of uses this particular thermodynamic applications. Also, just one second. What did I press? Also, the Pearson has created their own site of this, but I'm going to talk mostly about www.thermofluids.net. So how do you create an account? You simply go to the website and click on this create an account button, and just very minimal amount of information that creates an account. Everybody gets 30-day access. After that, generally educators write to me and their account become permanent. So this is pretty easy process. And just one more thing about help everywhere. So you will find, so let me first log in as myself. Oops. Okay, there we go. So once you log in, you can multiply your tabs. You don't have to log in again. Oops, I don't want to get out of Zoom. Okay, so I created 3 different tabs, so I go back and forth. So let's see. So we'll start with the different modules. I'll just quickly review different modules. First is the table modules. What we have here, all the modules are accessible from the bottom. These are the different tabs, as you can see. And the question mark everywhere is a help. If you put a question mark, it will give you context-sensitive help on that particular page. So let's take a look at the property tables. Everyone here is very familiar with tables. Essentially, if you click on, say, any table, and you'll see the numbers coming over here. And the tables are organized according to different models. These thermodynamic models kind of captures different kind of fluids. Here is a PC model, phase change model, such as H2O or ammonia, which changes phase. SL means solid liquid model, PG means perfect gas, IG means ideal gas, etc. But so the traditional table, let's say we have a superheated table of steam, and let's take a quick example. Suppose in the olden days, we had to interpolate. So for instance, we had to know at 0.01 MPa and 110 degrees Celsius, what will be, say, enthalpy. So our teachers used to tell us how to interpolate between tables, etc. So this job has been made easier now. So if you click on, see, I click on a table, it appears below. And if I click on the app, it will appear above. So suppose the question I just posed, what will be the interpolated value of a pressure, let's say 0.01 MPa and 110. So 0.01 MPa, we can just type in 0.01 MPa. And 110 degrees Celsius. If you calculate, it will okay. Any demo goes that way. Okay. Anyway, so I will just carry on right now with the PowerPoint, which is right here. So for the sake of time. So when you do a demo, when you do yourself, you'll see that once you put the numbers here, in this case, 6 MPa and 370 degrees Celsius, it will produce, let's say, enthalpy 3096. And if you do interpolation at 370 degrees, you'll get 3096. In other words, this calculator can teach students how to interpolate quickly by just guessing the number. In the animations module, what we have is that there are 16 chapters of animations. You can just go and browse the animations for instance, if you go to a steam power plant and modified cycle, let's say, and for instance, this is with one feed water heater. The nice thing about these animations is that as the fluid passes through turbine here, for example, it shows how the state point moves in the TS diagram. And also the corresponding equation comes up here. So it's going to the condenser. You can see the condenser heat transfer formula coming over here. And the moment you click here, this slide bar appears. It's something like watching YouTube. You can go back and forth and pause somewhere, or you can step through or play backward. All these, all these facilities are there in every animation. Some animations are quite sophisticated. It has a number of pages. So they're very useful. And as you can see, there are 12 chapters of animation. So if you go to animation chapter, you can see there are 16 chapters of animation. So there are sophisticated concepts such as, say you're deriving speed of sound. Even that can be done just by an animation explaining how the wave propagates and how the formula is derived. Fundamental things such as if you go to governing equations, and energy balance equation can be derived just through animation, that how the rate equations for energy can be derived by watching a system interact with its surroundings. Okay, so enough about animation module. It's kind of almost obvious. The interactive module, again, I'm just going to explain where to get it. In the interactive module, it's like essentially it's almost like an animation on steroids. So you go to say, understand device, a particular device. Suppose you want to learn about pump, then all you have to do is go there, and the default values are such that you can calculate and even the device with the fundamental default values, and then you can plot. You can click the analyze, and a parameter, in this case the pump efficiency, is being varied from 50 to 100. So in other words, someone can go and learn about a device even before learning about the theory of the device through parameter, that how, and these are real calculations, say in a turbine, you're changing the inlet temperature, how that affects the work transfer, the work produced by a turbine. So once you have a feel for that, understanding theory become more interesting for many, many people. So this is called interactives, but which doesn't require much background knowledge. Let's also go over the problems module, because it is quite an involved module. Just to give an idea, so you go to the problems module, you will see problems are organized again into 16 chapters. If you open a particular chapter, let's say a steam power plant, then as you can see, there are animations, as you can see, the problem statements are given. And it's kind of linked with, schematics are linked with animations, so that the animations have double use, animation chapters, but also it is linked with problems. So you're solving a problem, one user can see the particular animation helping understand the problem better. Also, while solving the problem, you can check your answer by clicking the problem number. We get a field. Suppose we just arbitrarily punch in some number. As you can see, these are wrong. I'm just arbitrarily putting numbers here. But more importantly, user can also look at the progress report. I mean, when you solve a problem, it's recorded. What problem one has solved, everything is recorded here. And another interesting feature, is the outcome-based learning. We all know that you do something for specific outcome, and in this case, the thermodynamics education is divided into something like 24 outcomes, and every problem is linked to one or more than one, a set of outcomes. So in other words, a practicing engineer can direct education towards learning a particular outcome. Suppose an engineer is employed in an HVAC industry. Then to meet that outcome, he or she can then pinpoint, solve problems that are geared to that outcome. So that's an interesting, another interesting feature. And then, and of course, educators and people with permissions can look at the solution. Here's the manual solution, and here's the how to solve it using test. So right there, there is a number of features. One of the very attractive feature for online teaching especially is that, another thing that not only the problems are organized according to chapters, you can customize. Suppose you want to just display only turbine. You can type in a particular, probably because it's under Zoom, but see, it worked. So all these problems are from different chapters, chapter 1, 2, 4, etc. That has the keyword turbine in it. Anyway, I just wanted to go over one more feature, which is very relevant. You can create a group. You can call it anything. Like I created a number of groups. As you can see, every time I teach a class, like ME 350, I'm teaching right now. I'm teaching what is called ME 450, Fall 21. I make group numbers named like this. And your email address is attached to that. So it becomes a unique group number, group name. So suppose once you created the group, that group name, if you share with your members, say students or your members in your group, and they come here and they join the group, they put the group ID and they can join the group. And once they join the group, what you can do, suppose I go and take a look at a semester, let's say ME 350 Spring 18, or I just wanted to take a random class, whatever that is. And then I generate a report, generate group report and say go. So what is happening is that essentially all the students that took that class, their reports are here, and I can sort them any way I like. Like suppose I can say sort them by last name by clicking here, or sort them by total number of problems solved, etc. Not just that, you know, we can for instance drill down into say, hey, you know, hey, let's see this student, how many problems, when these problems were solved. So we can go down, and so therefore it is very difficult for someone to cheat in the classroom. Suppose you give some assignments and it's due within a certain time. You can even check if somebody solved all the problems in one shot. That means they copied the answer probably. And you can filter them in different ways. So this is a pretty powerful problems module. We are working on a new feature that one can create a test online now using this feature. Okay, so this is in short, in a nutshell, what problems module has. And with that, I want to go to the most important module, which is the test step modules, workhorse of this entire website. So let me start with something very simple. So as you can see, the test step module is essentially a tree of different calculators. You can always go point put the pointer over a node, and that will display some information about at the top about what this module is about. So let me start with something very, very rudimentary. So basic tools, and I'll show you how all these complicated tools, such as even the chemical equilibrium solver, they all are building up on each other. So this is the simple calculator. Notice that if I click on any node, it goes, suppose you click on HVAC, it goes to a similar page, which are hands-on examples here. There are videos of solved example right here. And on the left-hand side is the app that you click to launch. So let me launch the simplest app, which is just a calculator, Descal. But it is essentially, it's like a programmable calculator. Suppose we say A in meter is, 3, and B in meter is 4. And we are suppose a right angle triangle, and we want to find the hypotenuse. C in meter would be square root of AM squared. Oops. Where's my 2 in power? Plus BM squared. So if I calculate, you can see that C is calculated. Of course, the hypotenuse will be 5 meters. But the nice thing about this is that obviously you can change one number because it's programmable. Suppose you say this is 5, and you can update it. And this mechanism of declaring variable will be added to all the app in the future. I mean, as we go on. Now let's try one more, the unit converter. I mean, everyone in the world has written a unit converter these days. Every engineer loves that. So anyway, so it's very simple interface. So you essentially select an area or angle, or suppose you want to convert. Suppose in Tripura, the land is measured in Kani or something. So you type in Kani, area will show up. And then suppose it's automatically from SI to English, and the top is meter square, at the bottom is foot square, as you can see. But suppose you want to know what is, for instance, a Kani. 1 Kani is how many feet square or how many meters square. So it's just very simple interface. So I was always curious because as school students, we had to read Tagore's Dui Bigha Jomi. I'm pretty sure most people are familiar with this. So how big is Dui Bigha Jomi? It's about 2,000 meters square, which is it's almost half an acre, I think, last time I checked. In USA, land is measured in acres, so 2 bigha is like almost half acre. So I don't think this guy was that poor, or people, even the poor people used to have good amount of land in those old days. Those who have read Dui Bigha Jomi must understand what I'm talking about. Okay, but this is not just about area. The measures can be quite, you can see they're sophisticated, such as you can do binary to hex, conversion from any base to another base, or such as coordinates in from lat long to all these different systems that are there, international system. According to each of them, you can convert one lat long to another. By the way, the default value of the latitude I picked up is Agartala latitude. Okay, so these are some very simple app, but let's show you what is state app. The state app, that's what I will say the real innovation here. Basically, if you think about it, when we think of numbers, these are individual numbers, scalars, and vector is a nice quantity that's 3 numbers together. You don't have to think about 3 numbers. It becomes a one entity, like a matrix. A huge number of numbers are now like just one variable. So similarly, in thermodynamics, you always fret over all these properties: pressure, temperature, thermodynamic property. There are different classes of property, material property. All these properties are, students and learner get lost in these properties. Instead, suppose we talk all the time about a state, that a system is always at a certain state whenever there's an equilibrium, and everything is about going from one equilibrium to another equilibrium. In that case, a state becomes one entity, and that's the idea here. So suppose this is the state. I can just, let's say I can say, so I picked a model here, by the way. Let me go back here. There's a system state and flow state. System state is essentially what it represents is a system with a closed boundary, and flow state represents a flow through a tube or something like that. So I had a specific example in mind because I wanted to build up. So let me go and see what values I picked. 4 MPa and 500 degrees Celsius. There's a reason for that. So we'll go. So to launch a flow state app, we go there. And at the end, everywhere you'll find a page with different thermodynamic model. For anything that changes phase, PC model is the right one, like steam table, etc., built in there. Solid, liquid, these are different gas model. These are different binary mixture model. And these are general mixture model. You can have anything made of multiple components in general mixture. So tonight, I'm going to just focus on PC model. So if I go to the flow state, and I said 4 MPa, so I can enter 4 to select MPa. Look, this is where the unit converter is coming in. And also you can have direct access to the unit converter from every app to go and change something. Okay, this is 4 MPa, and I forgot what was the other information, 500 degrees Celsius. So we go, put in 500 degrees Celsius and calculate. So we have calculated the state, and if you go to the graphics panel, you can see where the state is. You can draw a constant pressure line through that state. You can draw a constant volume line through that state. So there is quite a bit of analysis that you can do, visualization you can do about the calculated state. And we have found enthalpy and entropy. A little better way to do that would be, remember the calculator mode I showed? You can put what information we know, and we can say, given information or given data, we can say P1 in MPa is 4, and T1 in degree C equals 500. Now, if I do a calculate, I have calculated these variables, and I can come here and I can say, okay, initialize this. Let's do a different way. P1 MPa, and I choose MPa, and T1 degree C. And then if I do a calculate, the same answer is calculated. But look, this is much more authentic in the sense that now we are not tied with hard numbers here. So you can come here and we can say, oh, instead of 500 degrees Celsius, what if the temperature is 600? Then I update the calculation here and then click super calculate, and everything is updated. Now T1 is more than the 600 degree. Once you move, take a look at this part, if you can see it in the small screen, if you move the pointer over T1, you can see that value shows up. So what I'm trying to say is that this shows, this is more powerful because not only the answer can be changed, I'm sorry, the what if scenario, the entire solution is now printed in a very legible manner. This is called test codes. It shows what information was given, given data, and then how the state was calculated. P1 is P1 MPa, T1 is T1 degrees Celsius, and that's how we calculated the state. And the report of the report appears in the output area, and the test code, this is what is known as test code, that appears in the input area. So this is called a flow state test step. We have just finished that. Let's go see how we build on that in a device app. So let's go. In this case, we have, again, the state we calculated 4 MPa and 500 degrees Celsius. Now let's use that as an inlet state to an isentropic turbine. Okay, so we'll launch, because this given data, I'll just copy. So let's go launch a test step. This time we have to solve a turbine problem. So as you can see, open system, steady system, and it's a single flow system. If you put a pointer over, it will show that this is the type of problems these are capable of solving. Again, we launched the PC model. These are the hands-on examples. If you come here, this is the app, which looks exactly like the state panel we saw before, graphics panel we saw before. But in addition, now we have a device panel, which shows the device, so where a state can be used in one shot instead of a properties. So we'll calculate the inlet and exit state. So given data, let state 1 be the inlet and 2 the exit. Then this is given. And what else is given? At the exit, temperature is 40 degrees Celsius. So exit temperature is T2 is 40 Celsius. So we calculate all this given data is known. We go to the state panel, P1 MPa, T1 degree C, and mass flow rate is given, sorry, m dot kg per second is 10. Calculate, I think I lost that. I have to do that again. P1 MPa, P1 degree C, and m dot kg per second. So state 1 is fully known. State 2, temperature is known, T2 degree C, and mass flow rate must be the same because the same flow is going through the turbine inlet and exit. And it's an isentropic turbine, therefore S2 must be equal to S1. So state 2 is completely known. You can see if you draw constant pressure lines through state 1 and 2, so you can see 1 and 2 are vertically aligned because entropy doesn't change. And you go to the device panel, that's the interesting part. These are the mass, energy, and entropy equations which are solved when I load state 1 at the inlet, is H2O, state 2 as the exit, H2O coming out now, and it's an adiabatic turbine, so Q dot equals 0. So I just click calculate to find the work, and that's what is wanted, how much work is produced by the turbine. So now that we know how to solve a turbine problem, you understand that we can just scale it up. We can add one turbine and one condenser, etc., to make a power cycle. So this particular problem 915, I think I alluded to that problem before. Let's go and see if we have time to solve it. Could you tell me, Shapun Babu, how much time I have left?
Subrata sir, another 5 minutes, if you could.
Okay.
It's going wonderfully well.
Okay, thank you. I'll try to, I'll not go over the details of this, but I want to just tell you that, just like we solved the turbine problem, you could go and start the cycle problem with the same PC model. And you can see now, in addition to the device panel, there's a cycle panel. So once you complete the cycle, then everything is calculated. Let me just quickly see if I can find the code that, give me just a second. Then I can reproduce the solution. I can just show you how to reproduce a complex solution. Okay, I think I found it. So what I'm doing is that the solution I did, I just pasted the code, test code that I showed. If I just click the load button, that should solve the problem and all the states will be calculated. 1, 2, 3, 4. In the device panel, state 1, device 1 is my turbine, device 2 is my condenser, device 3 is my pump, and device 4 is the boiler. And as you can see in the cycle panel, we calculated the thermal efficiency, we calculated the net power. And if I go back to the test problems where remember I introduced the problem in the beginning of the talk, it was this particular problem. So let's see if we solve the problem correctly. I mean, I just quickly went over. So this is the efficiency that we calculated. So if we come back here and type in the efficiency, I'm just control paste, create my answer, that's correct. Similarly, I can put the power produced and that will be obviously correct too. So this is how complex problem can be solved. I just want to say just a couple of words, the last couple of words, that doing what if study is so simple, because now that we have a structure of a power plant, we can go there and we can just change. If we say, hey, the temperature was not 500, but 600, the maximum temperature, you calculate and then you super calculate, you come back to the cycle panel, you can see that efficiency has increased to 39%. So you can do a parametric study in this manner quite easily. So this is just, just one specific example. There are many other apps built on this. For instance, these are closed process apps from which reciprocal auto cycle, diesel cycle apps are made. And then from the open steady apps, there are many more than, say, turbine pumps, etc. Single flow system. We have mixing, non-mixing systems. And then finally, you can do vapor power cycle, which I showed, vapor compression refrigeration, gas refrigeration, HVAC. And the chemical equilibrium app is a very powerful app that you can produce emissions calculation with that. And gas.
আজকে তো কোনটারে শুধু স্যার মৌলিক রিলেশনটা দেখবো আর এনসি শর্মা কোনটারে সুগন্ধি দিয়ে দেব
সুবিনিয়ার প্রোগ্রামটা দিয়ে দিও, একটা প্রসিডিউর দিয়ে দিও।
এই চিন্ময়দা,
হ্যাঁ,
মিউট করে রাখো কথা বলার সময়। Srivastav sir, most probably he has lost his
Yeah, it seems
Yeah.
he is. Yeah. So shall we go ahead then? Has
just 1 minute, right?
Professor Professor Avinash joined?
Yeah, he has joined.
Yeah.
Yeah, I'm available.
Yes.
My apology. I think I got disconnected somehow. Hello. Oh, I'm still the host. Okay.
Sir, please
Hello?
share your screen, sir.
No. Just
Yeah, I'm kind of done with what I was doing. Just 1 second. I don't remember exactly when I lost. I was trying to conclude. Share screen. Yeah, so I was trying to show my final screen with a quote from Du Châtelet. She was one of the pioneering women in engineering. She translated Newton's, Isaac Newton's Principia to French. And one of the things she did was figuring out the kinetic energy by dropping little balls on mud, and seeing that the damage caused by a dropping ball does not go with momentum. Everything at that time was momentum. Everything is proportional to momentum. And she was so surprised. She's saying, why in the world? Well, the graph looks like it goes with velocity square. The damage goes with velocity square. And she was so stumped. And she had all these physicist friends, and they will not even look at her. Like this famous quote from Voltaire saying that a great man whose only fault was being a woman. Imagine how far we have come. And I wish that all mechanical engineering book will, give her the proper credit, someone who invented or discovered the concept of energy. Thank you so much, Dr. Bhowmik, for giving me the opportunity. And thank you so much, my panelists and all those who are attending and will be listening, that this site is there and it is ultimately it will be made available free once we have a cloud-based system. Right now, it's not totally free because the load becomes so high if it is free that our server goes down immediately. That's why we put some barrier. But for any Indian who wants to, use the site, it's definitely free for all Indians. Thank you. So I'll stop sharing and hand it over to the panelists.
Right. Thank you, Professor Subrata, for a wonderful exposition on the website Test Labs. It's almost everything under the sun as far as thermodynamic studies are concerned. So thank you very much for your wonderful talk and demonstration on this Test Labs. We hope all educators, students across the world would be benefited, are being absolutely benefited with this great contribution of yours. Thank you so much, sir. It's time to move to our other distinguished panelist, and Professor Avinash Agrawal. Yeah. So Professor Avinash Kumar Agrawal is our panelist, and we take great pleasure in welcoming Avinash sir. He is a mechanical engineer, tribologist, and a professor currently at Department of Mechanical Engineering of IIT Technology, IIT Kanpur. He is known for his studies on internal combustion engines, emissions, alternate fuels, and CNG engines, and is an elected fellow of the American Society of Mechanical Engineers, Society of Automotive Engineers, National Academy of Science, Allahabad, Royal Society of Chemistry. You name it, and you will find Professor Avinash there, right? He was also awarded the very prestigious Shanti Swarup Bhatnagar Prize for Science and Technology by Council of Scientific and Industrial Research in 2016. He has also been based upon prestigious J.C. Bose Fellowship of Science Engineering Research Board. And he also happens to be one of the top 10 highly cited researchers of 2018 from India. Professor Agrawal received the Young Scientist Award of Department of Science and Technology in 2002, followed by Career Award for Young Teachers of the All India Council of Technical Education, AICTE as we call it here in our country. He received the C.V. Raman Young Teachers Award of the IES Group in 2011 and Nasi Reliance Industries Platinum Jubilee Award of the National Academy of Science in 2012. The Indian National Academy of Engineering honored him again in 2012 with the Silver Jubilee Young Engineers Award, which was followed by Rajiv Goel Prize in Physical Sciences in 2015 from Kurukshetra University. And we already talked about the most prestigious Shanti Swarup Prize, one of the highest Indian science awards, which he bagged. So a highly decorated professor, educator, who has contributed immensely. I take great pleasure in presenting to you, Professor Avinash Agrawal. So kindly
Thank you, Professor.
Continue.
Thank you so much for your generous introduction, and thank you to Professor Swapan Bhaumik for inviting me. He's a dear friend and collaborator. So I'm very happy to be here. And Professor Srivastava, how much time do I have to speak? How much time you have for the session?
Around 25 to 30 minutes. If by 10:30, if you could close, we'll be grateful, sir.
Yeah,
The time
so 10:07. So I'll try to finish in 20 minutes, and then if there are any questions, I can take.
Fine. Thank you so much.
So I hope you can see my screen. Can you see my screen?
Yes, sir. Yes, sir.
Okay, so today I'll be talking to you about future prospects of green and environment-friendly methanol economy. And I would just like to give you a little bit of a background that, of course, in India, we are always in search of energy. India is a growing economy, which is one of the fastest growing economy in the world. And as a result, our energy requirement is going up. And we are always looking at energy sources which can, help us reduce our imports and so on. So just as a background, today, just like the world, India is also facing these three mammoth challenges. These challenges include depletion of natural resources. We have only 10% of the petroleum coming indigenously, 90% of it has to be imported. And then, what is happening is that these products, when we burn in different applications, such as, vehicles and generators, construction machines, mining equipment, they actually get converted to CO2 and they are put into the environment. So apart from creating, global warming effects all over the world, it is also creating urban air quality issues, especially in the densely populated cities such as Delhi. The urban air quality now at this point in year is one of the worst in the whole year, and it is by no means it's decent to actually live in. And part of it, not the whole of it, but part of it is also contributed by the engines and automobiles that we run. So can we do something about it? But before we do something about it, I think it's time to look at the fairness of the energy distribution and who is consuming what. So if you look at this pie chart here, this is a global energy chart, which tells that, how much petroleum energy, how much oil in the world is being consumed by which country. So you look here, 26% of the global oil is consumed by United States, 6% by Japan, 6% by China, somewhere here, India at 2.6%. So if you compare India with US on a per capita basis, US has 1/4 our population. They consume 10 times more total oil. So on a per capita basis, we are consuming less than 1/40th on a per capita basis compared to developed world, which could include even the European Union and things like that. So I'm not saying that we should be consuming at the same level as the West or US, but what I'm saying is that we consume fairly less amount of energy on a per capita basis, and therefore our footprint contribution to the CO2 emissions is also on a per capita basis very, very small. And this has to be factored in whenever we go for any climate negotiations. Now, if you look at the energy graph, how the global energy has shaped and how it is going to shape. So on the y-axis, you have total energy here, and this is a time span of about 100 years. So for the first 50 years of the last century, the energy demand grew at a rate of about 4% and then about 3%. And around 2025, by this time, this whole last 7,500 years have been powered by mostly petroleum, liquid petroleum oil. So now the wells are going to saturate. So by 2025, probably the global petroleum supply, liquid petroleum supply will saturate. And then it will taper off because we would have already consumed most of the liquid petroleum. But then our energy demand will keep on increasing. So how do you meet the gap? And obviously this gap between the demand and supply will not only create havoc, this will create wars, this will create all kinds of undesirable situations. So what will be possibly done is that for some years, maybe 10, 15 years, the lot of energy will be contributed by gas, natural gas. So, natural gas will satisfy our energy requirements in future, but we will have to ultimately switch to unconventional sources of energy, which somehow or the other derive their energy or their origin from sun. Could be wind, could be solar, could be any other form. So basically, the point that I'm trying to say is that we are around 2021, and we have about 10 to 15 years to make sure that all our unconventional sources of energy become economically viable. And that's going to be a big challenge to the scientific community, to make these unconventional sources of energy viable. Now, if you look at the transport system space, this is a very, very noisy space. You have road, air, marine, and rail sector. And these are very complex systems, and they actually contribute a lot to the GHG emissions. And it is estimated that, they contribute about 23% of the GHG emissions to the global portfolio. And they compete, the projection in the world is that entire GHGs are contributed by the transport sector, but that is not the case. It's about, different surveys say 16% to 23% is what is contributed by transportation. Rest of it is from construction, from industries, from agriculture, from the natural sources and things like that. So we contribute about 23%. And having said that, it needs to be reduced. So to take care of this, there are a lot of things that are happening in the transport space. There are new technologies coming up, new fuels coming up. There's new types of players, because now the cars are not just manufactured by car manufacturers. You have Apple cars coming, Google cars coming, and then you have Teslas coming. So there are new types of players that are entering into this space. And then government wants to create, jobs. They want to ensure that energy supplies are reliable and so on. And they want to somehow link agriculture to the transport sector as well. And then there is customer behavior, younger and younger population want, more and more faster cars and things like that. And then you have other exogenous factors such as, economic viability and things like that. And this transport sector, apart from the environmental impact, this also has social impact, because it affects, how many jobs are created, and so it has impact on the poverty reduction and energy security and so on. And then obviously all this has an economic impact. So it's a very, very complex system. Whenever we want to introduce any new technology, any new fuel, all these factors have to be kept in mind, and then accordingly. Now, there was a study done by Volvo, and they said that, whenever you want a new fuel to be adopted in any new engine, you have to basically take care of 7 important factors, which include basically the climatic impact. What is the energy efficiency of the resources that you are going to use? What is the land use efficiency? This is very, very important. How much land is required for growing that kind of energy or primary feedstock? What is the potential of the fuel? How much market penetration it can do? How much vehicle adaptation is required? Do you need to change the entire fuel, powertrain, for example? Engine has to be replaced with motor or things like that. What is the cost of the fuel? What is the infrastructure for producing fuel? Not only for producing, but also for distributing. So these 7 factors are extremely important. And whenever we propose any new fuel, it has to be evaluated on these 7 factors. So as I said, this is a very, very new, busy space. So a lot of fuels have been advocated all over the world. People talk about alcohols such as methanol, ethanol, synthetic diesel, biogas, biodiesel, DME, hydrogen, biogas, etc. All these are being talked about from time to time, but they need to be assessed on a more realistic fuel. So I think the future outlet, as I see from here, it looks like the transportation fuels in the future will be primarily liquid fuels. They will be made in refineries. And why they will be liquid? Because, other than nuclear fuels, there is no other substance on this earth which packs so much of energy. Gasoline and diesel, they pack 32 to 36 megajoule per liter of volume. You will not find anything else other than nuclear energy. So they are extremely dense fuels, and it's very difficult to replace them with anything else, because then we will have to look at the energy density factor. And that's going to be extremely challenging. They are very easy to transport, they are very easy to store, very easy to handle, and there are established protocols, and you hardly see any news of any accidents happening when they are transported, they are stored, or they are handled, compared to the amount of energy that is handled by these extensive distribution networks for the world. Now, if you look at where the motorization is going to be, so this is a global outlook. Again, on the y-axis, you see billions of vehicles, and on the x-axis, you see a time span of about 50 years. So if you look at the America and Europe, they are more or less flat lines. I mean, they already have close to 911 cars per 1,000 people. So there is not much of scope of growth there. The main growth is going to come from this segment. And this is basically China, India, and Asia. So basically going forward in the next century, India and China are going to be the vehicle of development for this whole world. This is where the most business will be. And this is where the most economic activities will happen. India, we have right now 23 cars per 1,000 people, compared to 800 to 900 in the West. So whenever we talk about any climate justice, or whenever we talk about any of those obligations, we have to also factor in that we can't deny our people mobility. Mobility is a fundamental right, just like right to live. Right to mobility has to be accounted for by developed nations as well. So this should be factored in, and this is where the most growth will take place. Of course, this is going to be noisy, because we will have to create a lot of roads, we will have to create a lot of infrastructure, but we need to give mobility to our people. So coming back to the 7 factors that I discussed, so here are the 7 factors, and these are the different fuels that I just mentioned. Include biodiesel, synthetic diesel, dimethyl ether, methanol, ethanol, biogas, hydrogen plus biogas, electric vehicles, hydrotreated vegetable oils. And these are the blocks which say whether dark one is optimal and lighter one is less preferable. So if you look at all these fuels are evaluated on these 7 factors. For example, if you look at biodiesel, it has some climatic impact. It has very good energy efficiency, but land use is very poor, because you need very large amount of land to produce biodiesel. So therefore, the potential is also rather limited. Vehicle adjustment is very small, because you hardly need to change anything in the hardware. Fuel cost is okay. I mean, it is still higher than diesel, but it's okay. And fuel infrastructure, same infrastructure you can use. So that way, each fuel is evaluated, and what clearly emerges out from this, one is this, which is having 5 dark spots and 2 less spots. So that means the vehicle adjustment, of course, if you have an EV, you have to replace the fuel, the engine with a motor. So it's a completely new powertrain. And the infrastructure, at least in India, is completely non-existent. But if you look here in this, if you look elsewhere, these 2, methanol and DME, looks to be quite all right. I mean, if you look at it, most of the things are quite dark. And so methanol and DME really have a good potential for not only for the world, but also it makes a lot of sense for India. And I'll talk about it in a little while, how we should be doing it. This is one slide which was presented by Chinese in one of the conference in probably Stanford, and I borrowed it from there. This just shows the plan of China of how they are going to go about methanol and DME. So this fuel, they call it fossil sunshine. And what essentially they are saying is that currently they want to produce the methanol and DME from coal, from petroleum, and from natural gas. So this they call as fossilized sunshine, because they will be using fossil fuel. And they will have some kind of a hybrid system. And in 2020, they did the deployment of large scale deployment of production of methanol and DME from fossil fuels. Okay. And then what they want to do is that they want to replace this fossil fuel with biomass. So all the municipal solid waste, all the agricultural waste, etc. They want to do first deployment of this hybrid system by displacing the fossil by 2040. And in 2050, they want to go for this biomass-based DME and methanol production system on a large scale for mass deployment. And what they want to do is that ultimately going forward, they want to displace even this. And what they want to do is they want to use the primary energy from solar and wind to use electricity, use that electricity for splitting water, produce hydrogen, and absorb the CO2 from the atmosphere. Use this CO2, react it with hydrogen produced by electrolysis, and then convert methanol and DME. And by 2070, they want to do the mass deployment. So once you have DME produced through this route, it will be GHG free because you are absorbing CO2 right at the time of production. You are actually removing the CO2 from the thin air, and you are using hydrogen, which is produced by CO2 free primary sources. It looks like a fantasy, but I think there is a lot of merit in this plan. And I think this is what India should also consider. And I think Niti Aayog is also seriously thinking on these lines, because by going for fossilized sunshine, you are creating the infrastructure for the methanol and DME production. Then you are just displacing the feedstock and converting it to run on biomass and municipal solid waste. And whole of the North India in the month of October, November, December, a lot of biomass is surplus in the fields. If we can put it, we can also get rid of these environmental problems. So this is on a nutshell, the big plan. And if you look at the properties of these alcohols compared to conventional fuels, so here is methanol compared to ethanol and gasoline and diesel. Most of the important properties are written here. The beauty of methanol and ethanol is that they have high octane number. They have high latent heat of vaporization. Therefore, the charge becomes colder when they are inducted in the engine, and therefore the NOx emissions are also relatively lower. The problem is that they have lower heating value, is about half than gasoline and diesel. So the range of the vehicle is going to be approximately half. And their auto ignition temperature is also high, which makes them inherently safe when they are used in the vehicles. Similarly, this table shows that, from a consumer point of view, energy density, storage cost, transport cost, and environmental impact becomes important. Again, here, the biomass, alcohols, hydrogen, and battery, these are all compared, and you can see that battery electric vehicle is very, very inferior compared to alcohols if they are implemented. So methanol, if you are having methanol, which is either produced from coal, natural gas, or biomass, or from the thin air carbon dioxide in the thin air, you can use them in the engines. It's as methanol or as DME. Methanol is having a high octane number. It has lower calorific value. You can use up to M85. What you can also do is you can also produce DME, and DME is a cousin of methanol. So basically, for producing methanol, you take two molecules of CH3OH and dehydrate it. That means remove water. So you are left with CH3OCH3. And it's an excellent fuel for diesel engine. It has a C10 number of 75 or so. And the C10 number of diesel that is available commercially in the market is about 51. So it has very clean burning characteristics. It's a good substitute for LPG and LNG. And it finds a lot of resonance in the government. You can actually, we already import a lot of LPG. So DME can be even used for our Ujjwala Yojana, where you can put it in the kitchen cooking fuel, etc. Methanol can be burned in the engine. Methanol can also be used in the fuel cells, in direct methanol fuel cells, and you can generate electricity. Again, that electricity can be used for including running the vehicles. And if you have methanol, you can even convert that into olefins. You can convert into gasoline, you can convert diesel. The processes are technically feasible, economically feasible or not, that somebody has to see, but it is practical. The challenges are that, it has lower heating value of 50%. So your range is less. And then, there is a possibility of formation of formaldehyde emission, SCHO. It's a natural combustion product. But then, if you have efficient catalytic converter, it's not going to be a major problem. There are some concerns that, if they spill in the water body while being transported through ships, etc., there will be some problems. So of course that exists, but then this problem also is overplayed by the environment. It's not really such a major problem as it is played. It is definitely corrosive to different materials, but then these are all engineering problems and there are solutions. People are working on it. And a lot of success in these areas, material compatibility of methanol has already been achieved. They can damage fuel lines, tanks and gaskets and even engine parts. So again, this area, these are also engineering problems. And there are a lot of material scientists which are working on to resolve these problems. One of the problems that remains is cold weather starting, because it's a single point fuel. It does not evaporate below 65 degrees centigrade. So there are strategies by which you can handle this as well. So this is just one picture that I made for methanol economy, just to show what is this concept of methanol economy that India is embracing. So here you have basically what we are saying is that, you know, all the biomass of different kinds, all the kitchen waste, garbage of the society, city garbage, this is all such a big issue in India. You collect all of that and you put it in a gasification plant. And once you gasify it, you produce carbon monoxide and hydrogen. And through a single stop process, you can produce methanol. And from methanol, you can either through this gasification, you can directly have DME production, or from methanol, you can produce DME. And once you produce these two, you can run variety of applications. And let me tell you that when you do this large scale on a commercial scale, there are estimates in India. Niti Aayog has come out with the figures, and they say that methanol can be produced at 14 rupees for 50 paisa per kilogram. That means 12 rupees per kilometer. So even if you take half the energy value, it's 24 rupees energy equivalent you will have for a gasoline or a liter of gasoline. So on a per megajoule basis, the energy will be about 50% cheaper. So all your conventional fuel engines and all your conventional applications can actually be transported back to DME and methanol. So obviously you can use it in different ways. You can use them as pure methanol, gasoline blends, diesel blends, and so on. So let's look at what is the experience worldwide. So I will talk to you about China. China is one of the big leaders, and you know, in 2014, this is a little dated number, but this is still 35 million tons of methanol they produced. About 5 million tons of DME they produced, and about 2-3 million tons of coal to liquid they produced. So just to put things in perspective, this is 35 million ton, and India's total energy consumption is roughly about 200 million ton. And this number, I'm sure, would have grown by now. So a substantial amount of energy of what China consumes is methanol. Okay, and they have a large number of vehicles which are tuned to methanol. There are more than 2 million vehicles, cars, buses, trucks, which run on methanol. And let me also tell you that government is not promoting. It's purely promoted by public at large, by taxi fleet owners, because the cost of energy is cheaper. If the environmental benefits are also there, that's an added advantage. But for the people, what matters most is the cost. So if you can give them a cheaper alternative, which is also environment friendly, it will make a lot of sense. So now China is running a lot of vehicles, and this is just a map of China which shows that, you know, these different blends, M5, M15, M85, M100, these are all commercially sold in different parts of the China. Similarly, you know, if you look at the DME activities, you know, there are significant methanol and DME activities outside China, in Russia, in UK, in Iceland, in Australia, US, and so on. So there are different places where some of these activities are going on. Similarly, you know, in Sweden, there is a plant which converts 1,000 tons of woody biomass per day, and about 4 lakh liters of biomethanol is produced. In Iceland, there is a plant by the name of George Ulla. He was a professor in University of Southern California, Nobel laureate of 1993 chemistry. He gave this concept of methanol economy. So here, what I just mentioned, you know, atmospheric CO2 to methanol plant. So this is already, you have a commercial plant which is taking out 5 to 5.5 thousand tons of carbon dioxide from the air, thin air, and it is producing 5 million liters of methanol per year. So this is all now, this has passed the pilot plant stage. In
Professor
Canada,
Avinash, if I could intervene, if you could conclude, it's great going, but time constraints are there. I'm so sorry to bother
No
you.
problem, sir. I can stop right here. Yeah. If there are any questions, I'll be happy to take.
I believe the time constraints are not permitting us to take questions now, but whatever questions that our participants have, they'll pass on to you, and we'll see that every question is answered.
Sure, sir. Definitely.
Thank you so much for a wonderful presentation.
Thank you.
In this era where we're all thinking that electrical vehicles are the future, there's a wonderful presentation by you which says that even the conventional fuels, methanol and DME, still have a lot of hopes for us, who could be cheaper, better, and environmental friendly as well. So thanks a lot for this insight which has been brought on this forum. Thank you very much, sir.
Thank you.
It's time.
Hello, Professor Das. How are you? Good to see you after a long time.
Yes, of course.
How are you doing?
Yeah, we are doing wonderful here in Chennai, except excess of rain.
Yeah, I saw that. Hope things will improve soon.
We now invite Professor Sarit Kumar Das as our next panelist. Let me have the pleasure of introducing Professor Sarit Kumar to all of us. Professor Sarit is a former director and professor at IIT Ropar, Punjab, and is currently on leave from IIT Madras, where he is professor in Mechanical Engineering Department and also served as its Dean Academics. He obtained his BE Mechanical in 1984 and ME Heat Power in 1987 from Jadavpur University, and completed his PhD in the area of heat transfer from Sambalpur University, and joined University of Hamburg, Germany, where he did his postdoctoral research in the area of plate and liquid metal heat exchangers. He has published 4 books and more than 250 research papers. He is a recipient of Dahl and Alexander von Humboldt Fellowships of Germany. He is a fellow of Indian National Academy of Engineering and National Academy of Science in India. He has been bestowed with several awards. Some of them are India Citation Award 2012 by Thomson Reuters, Professor K.N. Sitaramu Award, and Medal for Excellence in Research by Indian Society of Heat and Mass Transfer. He has also been awarded the Peabody Visiting Professorship at the Mechanical Engineering Department, Massachusetts Institute of Technology, USA. He is the editor-in-chief of the International Journal of Micro and Nanoscale Transport and an associate editor of the journal Heat Transfer Engineering. His current research interests include heat transfer in nanofluids, microfluidics, biological heat transfer, nanoparticle-mediated drug delivery in cancer cells, heat exchangers, boiling in mini microchannels, fuel cells, jet instabilities, heat transfer in porous media, and computational fluid dynamics. So it's over to you, Professor Sarit.
Okay, let me share my presentation.
So,
please allow me to share.
sir, please. Okay.
Sir, please share, sir.
Is it visible?
Yes, sir. Screen is visible, sir.
Okay. Okay. So let me start. Thank you very much for giving me an opportunity to present this particular work. We just heard a very wonderful lecture from Avinash, who gave an overall picture in one sector of the energy problem. So there are 2 types of lecture. One gives you overall picture of an area and relation to research. The other one is research itself, take up a more narrow topic and talk about what is the state of art, where the technology is going. So my lecture today, I have very deliberately chosen, because last 5 years as director of IIT Ropar, I am tired of giving these overall pictures. So because every time director speaks, people expect to give an overall picture. So now I am a professor of IIT Madras, and hence I will go to a technical lecture completely. Now the thing is, I do not know why Swapan called me, because young people like Avinash, Swapan, they are the people who will take the technology forward. Old people like me, who are not yet in the twilight time of my career, but still, I think we are the senior ones, if you tell in a very mild term. Seniors have got an advantage, what is called experience, but sometimes that is atrocious. They also have the problem of being reduced efficiency, trying to repeat the same thing, and so on. So aging has got its own problem. And that's the thing that I want to bring out in today's lecture. What kind of a problem aging has got, so that not only we are concerned about the aging of heat transfer, I am myself concerned about my aging. So with this, let's come to the topic, which is nothing other than the heat transfer for electronic cooling. Now, this is a subject which is going for last, I don't know how many years, 20, 30 years. Right from the beginning of my career, I am hearing electronic cooling is important. But let's first give the well-known facts about electronic cooling. Everybody knows this, what is called the Moore's law. It's about 18 months, the number of transistors in a circuit double. In our integrated circuits, the number of transistors in a given square inch is doubling in 18 months. And as a result of that, if you see from 1970s, when we had those two, you may not be knowing, today's generation do not know what is 286, 386, and 486. Those were the names of the microprocessors. We used to be proud that I have a 486. But if you talk about the kind of speed they had or the storage they had, people will laugh. Your watch may be having much more than a desktop computer in those days. And if you look at the Pentium came in when I was doing my postdoc, and it was a big deal. But you see where we have moved from there. The problem is this curve is not linear. If you look at it, we were expecting that this will go in this direction, but it is already bending. What does it mean? It means that we are not able to put the same number of devices.
So the screen is not visible.
Sir, your desktop screen is, laptop screen is visible.
Your presentation is not visible.
Presentation is not.
Shared a wrong screen.
Please, just 1 minute. Then I will go to my PDF version. Is it visible now?
No, sir.
No, same. You have to share your, go to the share and then select the right file.
Yeah, it's visible.
No.
It's visible?
Yeah.
Okay.
Right.
Okay. So what I was trying to tell is this curve. If you look at the left-hand side Moore's law curve, it's not a linear curve. It is bending towards looks like a saturation. And what is important, the saturation is not due to electronics. Electronics can put even more. They are coming to nano devices, they can go to molecular devices. But the problem is that the more number of the devices are put within a given space, what happens? More heat is generated. And how to dissipate that heat. And so we the thermal engineers who were 20 years back were thought to be the fringe, players. The main people are the electronic device making people. Today, we have come to the forefront because without us, the electronics cannot improve anymore. And if you look at what is the reason, you look at the power density, that is watts per centimeter square. From 1970s, now you look at the curve, and this is not a linear curve at all. Where we have gone actually is the power density, that of the nozzle in your chip, that of the nozzle of a rocket, a space launch vehicle. You do not feel that amount of heat, but because the area of cross section is very small, the flux is very high, and that needs tremendous amount of cooling. We must understand. And so what are the options for cooling? These are the newer options that people are thinking about: falling film, liquid jet impingement, spray cooling, capillary pump loop, curved channel cooling, and micro channel flow cooling. These are various options. Each has got its advantages and disadvantages. I won't go to it. Some of the devices, typical micro channel heat sink. One of the people who have worked is Professor Suresh Garimella of Purdue University, and this is the device that they suggested. And basically, what we are trying to say, the central question is this, that the micro channel heat sink run for a longer period when used in engineering applications. So why micro channel? Because see, today the way the chips are cooled, actually they put a heat spreader, and by heat spreader they take away the heat from the chip to a distance, and then with the help of air we dissipate the heat. Now with micro channel, what they are saying, that on the chip itself they will cut micro channel. One side will be the device, electronic device, the other side of the chip will be micro channels. So the liquid will flow not somewhere in a far distance, but it will flow on the chip itself.
Professor Pradip Chaturvedi,
Excuse me. Someone has to switch off the speaker. Okay, so what we are trying to say is the cooling on the chip itself by microchannel. So now the problem is that if you go on cooling with microchannel, the problem of aging. Suppose you have got microchannels made in copper. What is going to happen after 6 months? After 1 year? Is it going to perform the same way? This is very, very important because microchannel, the system needs to be very, very clean. Otherwise, with time, if there is a deterioration, there is a more chance of failure of the microchannels and the heat dissipating device. And so the main objective is to find out the effect of copper aging on flow boiling characteristics of a mini channel, because see, liquid single phase cooling is already gone. Every laptop is today cooled with a multi-phase cooling with heat pipe. So to investigate the aging of copper surface, we are also to look at the boiling efficiency along with the critical heat flux in microchannels, and to record the changes in the surface characteristics due to aging. So essentially, in this lecture, what I am going to cover is this, that I'm not going to cheat now. I'm going simple two-phase heat transfer in microchannels and try to find out with aging of the channel how heat transfer characteristics, pressure drop characteristics, and critical heat flux characteristics of microchannel change with number of boiling operations, or number of months, or number of days that the boiling operation is going on. So to do this experiment, we have here we are showing only a single channel. You can see this channel which is cut on copper like this with a micro machining, and then we put that micro channel here, and then the fluid is in here, fluid is out here. At the bottom of the micro channel, there is a copper block heating block. So this is the assembly. So this is what is the cartridge heater. This one is the copper micro channel. And then there is a cover, polycarbonate cover. And this is the block in which it is housed. And, it looks very simple to put it and do your experiment, but it is extremely difficult to machine it and to assemble it. I remember one of my students, a couple of years back, spent 1.5 years simply to arrest the leaks in these kinds of devices. So these are not easy to do experiments. It looks simple. And this is what are the dimensions of these devices. They are of the order of 300 microns, 600 microns, and 1 millimeter, that is 1000 microns. The hydraulic diameter I'm talking about. The depth is even less. It is of the order of 200 microns to 700 microns. And these are the heaters that we have used. Now what we have done, this is the whole loop in which the whole devices are put. But what is important in the microchannel, we have to measure temperature at various points. Something like 7 to 10 thermocouples, and it is in these cases putting the micro thermocouples into the channel at the bottom of the channel and measuring the temperature correctly is a tremendous challenge. It looks very, very simple, but it is not. So what we do, we let the liquid evaporate in the microchannel, and then there is a condenser run by a chiller where we condense it. Then we vent. If there is some gas left out, we vent it, we bring it back, we do the degasification, and with the micro gear pump, we make the fluid to flow. Coriolis mass flow meter measures the mass flow rates, and all these are very, very important because you see, when the flow is very small in microchannel, what will be flow? I mean, microliters kind of things. And so if there is an error of couple of microliters, the percentage error blows up. And hence these experiments are very, very fine-tuned experiment, very difficult. Even getting, the baseline experiment is very, very difficult. Then we use a preheater because we are using boiling. We cannot have subcooled boiling here because then the whole microchannel may be subcooled boiling. That's why we use a preheater, and with the help of that, we bring the liquid for boiling inside the microchannel. This is some kind of, the huge number of equipment that you have to maintain to carry out these experiments. Now, in any experiment, first we have to do, in particularly these kinds of experiment, is my experimental setup okay? Are the known things reproducible? And this is exactly what we have done with single phase. That means we have not come to boiling in this particular curve. We are carrying out single phase experiments, and single phase experiment means we are heating, but we are heating to a temperature of say maybe 40, 50, 60 degrees maximum. So what we are trying to do here, we are trying to find out that at 0 months, 2 months, 4 months, and 10 months, whether there is effect of aging when single phase heat transfer is taking place. And what we find, it's almost a negligible aging, because this is the standard correlation, the Shah's correlation in microchannel. And then you look at how it is changing from 0 months to 10 months. It is essentially within the limits of experimental error. So you cannot say anything has really changed. There is, if you look at the Nusselt number between experimental and predicted correlations, the deviations is 18 or 17%, and with other correlations it may be 40%. But in general, in microchannel heat transfer, these kinds of deviation from correlations are very, very common. So we are in the correct region. We, of course, it follows one particular correlation better than others, but then this is the friction factor, and this is the Nusselt number. But in both the cases, what is visible is that the deviation over 10 months is not much. So single phase heat transfer. So the first conclusion that we can make, there is hardly any aging effect of flow inside microchannel when the heat transfer is single phase, when the two-phase heat transfer doesn't take place. Next, we move to the two-phase heat transfer. Now, in two-phase heat transfer, there are various challenges. One of the challenges is this, that like normal heat transfer experiment, two-phase heat transfer experiment in a tube, we cannot consider microchannel heat transfer with one saturation temperature. We cannot say average pressure of the tube is so much, average pressure of the channel is so much, so give one number to the saturation temperature. Because in microchannel, the pressure drop is large. And because of the large pressure drop, because the channel is small, for the same flow rate, the pressure drop will be much, much larger. The saturation temperature changes. So what we have assumed here, which is a reasonably good assumption from literature, is that the saturation temperature varies linearly from inlet to outlet. So this is how our saturation temperature varies. That means the boiling point itself varies. And then outlet vapor quality by energy balance, we find out. Heat transfer coefficient, we find out by local world temperature, because world temperature we have measured locally at 7, 8, 10 locations. And from there, we can find out the local heat transfer coefficient. And the overall heat transfer, average heat transfer coefficient, we find out by taking integral of that. Now, this is how we reduce our data. And now, let me put, in months interval, how the heat transfer changes. Now, this is Q versus delta T. Boiling traditionally is represented by Nukiyama curve. And you can see in Q versus delta T, in 0 months, 2 months, 4 months, and 10 months, you can find out that the changes which are taking place, these are at different mass fluxes. And for the same, instead of Q versus delta T, if I put heat transfer coefficient versus Q, there also you can see how the difference is coming. Now, we can go ahead up to 10 months and find out how things are changing. Now, what we are seeing is there is a substantial change in the heat transfer coefficient. And it does not change so much with the mass flux. It changes with the heat flux. Now, this is something which is known about microchannel. Microchannel boiling does not work like flow boiling. Because, what is the basic difference between flow boiling and pool boiling? Now, this I don't want to teach here. Let me tell you that my book on two-phase flow is coming up. Probably the interested people can look up at that one. But what I'm trying to say is the basic difference between the pool boiling and flow boiling is this. Pool boiling, or what we call nucleate boiling, is dependent on heat flux, whereas flow boiling is dependent on mass flux. But what we are seeing here, that at various mass fluxes, the difference is almost nothing. Whereas at various heat fluxes, the difference between the heat transfer coefficient is large. Which means microchannel flow boiling does not behave like flow boiling. Microchannel flow boiling behaves like nucleate boiling. Now, is there an advantage towards that? Yes, there is an advantage that nucleate boiling is known to be the best kind of two-phase boiling. And so microchannel doesn't only give, on one hand, greater area, because for the same flow rate, if the channel diameter is smaller, the surface area increases. And if the surface area increases, heat transfer increases. So on one hand, the heat transfer increases due to surface area increase. But on the other hand, the heat transfer characteristics are better due to the nucleate boiling nature of heat transfer. Now, you are carrying out flow boiling, but you are getting nucleate boiling kind of a scenario. And this is the uniqueness of microchannel. Now, that's the reason why two-phase flow in microchannel has become so much an active area of research, because this is probably the future of electronic cooling. Or not only electronic cooling, there are other devices which are going to be important in future. Things like, say, cooling of laser. We have got laser devices for almost everything, from electronics to manufacturing to medical surgery. And the lasers need to be cooled. And these lasers are quite often very small in dimensions. For example, for surgery, the lasers which are used, they need to be cooled. And microchannel two-phase heat transfer may be one of the major applications of cooling in these kinds of cases. So now if you see months interval, you can see the aging is taking place. I was talking of simple microchannel heat transfer earlier, but now I am looking at how it changes with time. And surely we can see, even at a given mass flux, with time, the heat transfer deteriorates. If you see that this is the pressure drop actually, if you look at 0 months, the lowest pressure drop. And if you look at 10 months, almost the highest pressure drop. Now, it essentially means that with time, the pressure drop increases. Now, what can be the reason for increase of pressure drop? One of the arguments can be that due to roughness. But you know, in microchannel, there's no turbulent flow. So pressure drop depends on roughness only in turbulent flow, not in laminar flow. So this is another fallacy, I would say, is to find out why the pressure drop is decreasing. Because the change in cross-sectional area is negligible due to modification of the surface. Yet, there is a perceptible change in pressure drop, although the flow remains laminar. So this is another thing. Whereas now you look at the heat transfer characteristics, and you can see, even if you look at day-wise, you can see there is a change from day 0 to day 6 or day 210. The changes are very rapid towards the beginning, but then it stabilizes. So aging at one point of time is very fast, but beyond a particular time, say a person like me, when I understand that I cannot run like a young man of 30 years, I stabilize and I want to, instead of running or jogging, which I was doing earlier, I start walking. So I understand this is my limit. Probably the microchannel also understands that, and they settle down to a particular heat transfer. Now, next is, if you look at the two-phase pressure drops in days interval, even here, the same characteristics, that it's a fast change towards the beginning, and then, out at 210 days almost, it stabilizes. That is, I'm talking of 6 months or 7 months. Now, two-phase heat transfer in mini channels. Now, when you look at mini channels, the changes are much lesser. So you look at, this is 1 millimeter, 1022 micrometer means 1 millimeter hydraulic diameter. And here you see that, again, the situation is different. The different runs, if you look at, the changes are there, but changes are found to be less than the previous case. And you look at this, run 1, run 2, run 3 are actually the, they are for aging. I have not given the number of days, but it is something like faster in the first part, and then there is large gap between the runs. But again, they show little effect and stabilization, and maximum change is only around 10% In microchannel, 10% is nothing because that is within experimental error itself. So what is interesting now, that the fast deterioration of the performance, both in pressure drop and heat transfer, is a characteristic typical of microchannel, not so much of mini channels. So there is, see, how do we differentiate micro and mini channel? There are debates how it can be differentiated, but more or less people think of the order of millimeters we can call mini channels, of the order of hundreds of microns we can call microchannel. And if we go less than 100 microns, we call it transitional. And then if we go of the order of 1 micron or below, it's nanochannel. So we are talking of microchannels, which are of the order of from 200 to 7 or 800 microns, which are practical. Why we are talking of this range? Because this is practical to be cut on chips for cooling. And in this area, definitely we have to face aging, and we have to know what those aging characteristics are. I know the time is coming to an end, I think, and so I will go faster. You can see that this is what is the SEM characteristics, confocal microscope images of the fresh channels, and after aging, after hundreds of, tens and hundreds of boiling, how they become. The microstructure change, even copper oxidation is seen from these EDAX pictures. And the other thing which is important, what is changing? Actually, what is changing? Why boiling is changing? It's because of weightability. You can see that this is a device to measure the weightability. We made measurements of, suppose before boiling, a drop looks like this on a copper surface. After boiling for a couple of months, it looks like this. That means it has become more weightable. And everybody knows that boiling is worse when the surface becomes weightable. Less the weightability, the boiling is better. That's why boiling is difficult in a new vessel. It is easier to boil on an old vessel because the old vessel, the roughness grows and the weightability becomes less. And you can see with time how the contact angles, these are the contact angles, how the contact angles come down. And I will go very quickly. These are the surface changes. These are the surface roughnesses which change. And you can see that the heat transfer is related to the contact angles. When they are, so the aging process which I am talking about, why aging takes place? Because of boiling repeatedly, what happens in microchannel, the contact angles change more rapidly. Because in this case, the protrusions are of the order of the channels, so they matter more. In a bigger channel, because protrusions are much less compared to the main flow, so the main flow can suppress those characteristics, whereas in microchannel, they cannot. And hence, the two-phase pressure drop also changes. And so I won't go to this one. This only shows that.
Harit sir, kindly conclude, sir.
Yes, I'm concluding.
Thank you so much.
Yeah, I'm concluding. So these are the microchannel heat transfer correlations. It shows that the correlations do not agree here, the existing correlations. So we developed our own correlation where contact angle is a parameter, and even critical heat flux. If you look at critical heat flux, actually does not change. So it remains as safe as the previous one. So the conclusion is there is a change in surface characteristic of copper microchannels over a period of time, which can be attributed to aging due to copper oxidation. The change of heat transfer coefficient due to aging depends on the boiling duration, number of boiling cycles, and not the time interval between them. And for range of parameters considered in the study, we have come to a boiling dominant region, and the deterioration of the two-phase heat transfer coefficient is like this. Aging gives to surface oxidation, increased weightability, and inhibition of nucleation. This is why the boiling characteristic change. The experimental study demonstrates that with proper cleaning of the surface, the two-phase heat transfer can be regained. And the final one conclusion is very, very important. This is no single correlation is available in literature. A new correlation has been proposed to predict boiling heat transfer coefficient based on repeatable data after 8 years. Thank you very much.
Thank you. Thank you, Professor Sarit, for a wonderful research and disposition before the audience. The silver lining which I could get from your presentation, sir, in this era of digitization, where electronics and computer science graduates or engineers are more preferred than mechanical engineers. You have rightly said that thermal engineers and mechanical engineers have good time and good prospects in future. So that's a wonderful thing to listen to you. Thank you very much, sir.
Thank you. Thank you.
We have had a wonderful panel. The last one is Engineer Pradeep Chaturvedi, who happens to be a very senior person and is in fact a friend, philosopher and guide at the Institution of Engineers, India. So welcome, Pradeep, sir. In fact, I would like, he doesn't need any introduction, but as a formality to this audience, I would like to speak a few words about distinguished engineer Pradeep sir. So he is essentially an automobile engineer and is a globally known energy and environment expert. And essentially, he is a futurist. He is a fellow of Indian National Academy of Engineering, the Institution of Engineers, All India Management Association, and several other professional institutions. His involvement with professional engineering activities are well recognized. He is Chairman, Interdisciplinary Coordination Committee of Institution of Engineers and member of the Steering Committee, Energy Sectional Committee, and Forum on Technology Foresight and Management of the Indian National Academy of Engineering. He is a pioneer in renewable energy sector. And to his credit goes the first installation of the renewable energy village in India at village Achaleja near Delhi, which is globally acclaimed. Engineer Chaturvedi has been involved with action-oriented innovative projects on sustainable development strategies, energy and environment, policy and planning in India and other Asian and Pacific countries, all under United Nations programs. Some of them happen to be the first time such initiatives, which have been acclaimed all across the world. Engineer Pradeep sir has been involved with the studies program of the World Energy Council since early 80s and has provided several vital inputs on many such studies. Under his chairmanship, an expert committee of the IMC WEC prepared a first ever report on energy dimension of disaster management in September 2006, and another study on sustainable development of Delhi for and beyond Commonwealth Games 2010. He has also chaired International Task Force of WEFA for writing the global report on sustainable energy engineering, which was released in 2009 at Kuwait. He has also conducted a study on energy intervention for attaining 175 gigawatt of renewable electricity in India by 2022. To his credit, have been several such projects, and he is a shining light as far as energy and environment in the perspective of our country is concerned. He has also been instrumental in drafting the Energy Conservation Act 2001 and Electricity Act 2003. So when it comes to energy and environment in our country and globally, Engineer Pradeep takes the front seat. So he has been bestowed with several national and international awards, has authored 8 books and edited 30 plus books on energy and environment. So welcome, Pradeep sir, and the forum is yours. Unfortunately, we have got to wind up the session. So about 10-12 minutes, if you could give your words of wisdom, it'll be great, sir.
Right. Thank you. Thank you very much, Professor Rakesh Srivastava. It's wonderful, and I'm really grateful for your kind words that you have spoken. This mechanical engineering convention is at an ideal time, at an ideal place, and is being done dedicated to the institution's cause. Very few people know that when I was the chairman of Delhi State Center in 2001-2, Mr. Devnath used to visit Delhi virtually every month and would spend so much of time, the energy that he showed. It appeared that he was the only engineer from the Northeast, but he would like to do everything for the Northeast in all faculties, although his specialization was civil. Also, we have the privilege of Professor Swapan Bhaumik, who is the chairman of CATE, and the amount of work he has done during last 2 years is remarkable. The last CATE agenda that he developed ran into 500 pages. That shows that how he has tried to find out where all institution can really look into and what all aspects can be looked into. So it was, although it is a momentous work that he has done. And Mr. Jagrup Singh, who is the chairman of the MCDB this year, from 2012 onwards, when we had started fighting for the AMI recognition, he has been holding the fort and really working 24/7, and just saying midnight oil is not sufficient. He's so dedicated. He is working with the lawyers, with the government officials, everyone. He's been trying very hard, and his work as a chairman of the MCDB has also brought laurels to the MCDB. This is why I said it's a combination, a unique combination of occasion where we find that all the best in the world are really joining. Those who have been associated with the Institution of Engineers these are the shining lights who will show that look here, institution has a lot of scope, lot of image, and their faith in the institution's capability to carry our message forward. And let me tell you, during last 2 pandemic years, Dr. Bhaumik had really geared up the institution's activities, taken every one of us onto the virtual platform. And as the chair of the International Coordination Committee, could also work with him, and we have come out, whereas others were sitting idle, we had come out with many of the important reports for the Institution of Engineers, involved the topmost of the scientists, engineers into it, identified the problem areas where the institution could really march into the new century. We came out with the centenary book, but then also how to march into the new century with the greater sense of pride with Make India program of the government, and where does the mechanical engineers and the engineering community as a whole really could be contributed. The Glasgow summit came in very handy, and this has just happened, and we have finished on 13th of November. It came out with many of these recommendations. As I said yesterday, the Prime Minister took the initiative to really point out as to where all he wants our engineers to really focus on the areas. He has set a goal, and where thermal engineering and the mechanical engineers all have a very important role. The 5 mantras which he presented at the Glasgow conference, the initial thing, and everyone was taken by surprise with the statesmanship that our Prime Minister showed. And this is where the engineers have to play an important role. The first will be to take the non-fossil energy capacity to 500 gigawatt by 2030. Second, India will meet 50% of its energy requirements from renewables by 2030. India will reduce the total projected carbon emissions by 1 billion tons from now till 2030. Fourth is By 2030, India will reduce the carbon intensity of its economy by less than 45%. And by the year 2070, India will achieve the target of net zero. I mean, he has presented a vision where India will go and where India should go. And this is now for the engineers to really interpret. And if you'll notice that in all these 5, what he called as the Panchamrits, really the role of the engineering community is far more important. The Institution of Engineers last year, I remember we had conducted a few webinars which were directed to these issues, and they really pointed out to many of these. We have also identified where all we have lagged. Now you see, very easy to say that we'll decarbonize, we'll cut down, should shut down our coal plants, and that is the way out. But then we also identified that over the last 15 to 20 years, say from 2001 onwards, the governments have put in some small monies into R&D, and the results of the R&D are really not telling us that we are reaching any breakthrough technologies which will take us to the global level, whether it is IGCC or any of these, you mentioned CCS or any of them. But then we have been tinkering with the smaller technologies and the engineering efforts, and we have reached a stage where we can really we really find ourselves still in a difficult situation. And since India has to catch up with the future, the Prime Minister has very eminently, as a statesman, put forth India's case in his first speech at the Glasgow conference, saying that we are not going in for the net zero by 2050, but by 2070. And the whole world was taken by surprise, but he was bold enough, and then he gave his reasons for it. Our investments into the coal sector, our investments into many other sectors are so intense, and his courageous move to tell that we are not involving ourselves into the methane lobby is another important thing. Some of us who had been in the 1992 Rio conference, you know, the Indian Agricultural Research Institute spent 1 year to counter what the Globe said, that the developing countries like India are emitting too much of methane through the rice fields. And India Agricultural University conducted tests for 1 year to prove. And ultimately we said that methane is not really emitted to that extent only from the rice fields, but there are many other sources. So the Indians had done it, but the outcome, if you look at the outcome of the COP26, because we have to relate our whole future engineering with the outcome of the COP, bringing the resilience in our engineering approach, bringing the flexibility. And we should also realize that the whole developed world is talking of the net zero, but we are also talking of the carbon neutral. Now we must realize the difference between the two. The net zero means that you can pollute at one end and compensate with it at the other end, and then you say that look here, and this is what the developed world is doing, that we are doing the net zero. The carbon neutral means that the whole process of your going from here into the development thing is carbon neutral. You're using the sustainable path, and that is the whole process of sustainability. And the Indian engineers have to really follow this whole path. Now, let me tell you, some of the people feel that as if Glasgow conference has been a failure, but you must see that it has shown the pathway, and which is to be followed by most of the engineering fraternity to make it a success. More than 40 countries, including major coal users such as Poland, Vietnam, and Chile, agreed to shift away from coal, but others who are deeply involved in the coal, they said that we will take some more time, and that's where we are winning over the thing. Now, the private sector also showed strong engagement with nearly 500 global financial services firms agreeing to align 130 trillion, some 40% of the world's financial assets, with the goals set out in the Paris Agreement, including limiting global warming to 1.5 degrees centigrade. In addition, there were 3,000 companies who have signed on the pledge with the Secretary General of the United Nations saying that we'll move towards the net zero. They said to whether the developed countries do it by 2040, others do it by 2050, or a little later. Fortunately, the US and the China also have pledged to dominate climate cooperation, although China did not participate. But then we are doing, there are more than 100 national governments, cities, states, and major car companies signed the Glasgow Declaration for zero emission cars and vans to end the sale of internal combustion engines by 2035 in leading markets and 2040 in the worldwide. Now, this again is going to be a major challenge for our thermal engineering professionals and for the engineers to see how you can move at such a fast pace from the fossil-based transportation onto the fossil neutral transportation. It's not that all that easy. But the power sector has been really one of the major areas where the thrust has been, the coal has been in use. And many people think that if the call is that, can we go in for the coal sector, stop the coal power plant? The international treaties where they say that we'll not go in for the new, let's not go in for the new coal plant, it simply means that such coal plants where the financial bids have already been opened, those are still being considered to be the power plants that will come in. But don't, if you have not done it, don't open a financial bid, don't go in for the new sector. But if you consider those where the financial bids have been opened or where the work has already been done, in India, it opens to almost about 100 gigawatts of coal-based power. Now we have been working. We were working in the subcritical power plants. We decided that we'll move on to the supercritical power plants to improve our efficiencies. We have borrowed technologies and the processes from the developed countries where the ambient temperatures remain around 25-30 degrees or low. And supercritical power plants really work very efficiently. But if they do not work at the maximum efficiency or the maximum plant load, they can be much worse than the subcritical power plants. And this is what we have found, that we had in the past. The government had put a pressure that only supercritical power plants will come. Therefore, we are expecting that some of these new overall systems efficiency will increase. The work was done in some places, but the quality of coal that we have after the government decided that in 2020 that we will be allowing the Indian coal to substitute for the imported coal. We are back to the stage where we find that Indian coal with high ash content and low sulfur content is really creating a more problem for many of the power plants. And although it works well for the subcritical power plants, but for the supercritical power plants, new technologies have to be evolved, and a big challenge for the thermal engineers into it. Let me also say that various steps are now being taken, but unfortunately the thrust is as if we have only to remove the sulfur from and make coal a pure source of energy. But that's not true. But some of the technologists feel that desulfurization would be one of the processes, but one has really to work. Our coal quality in India is very poor. The calorific value range at about 4,000 kilocalories per kilogram. And this average has been decreasing over time. That's going to be the future challenge. And therefore, some of the technologies that we have to really work are improving efficiency and operational performance, the coal washing to really bring it at par, and then many other changes that requires to be done. And we have to push the private investment in coal production, or the Coal India Limited has been pushed into it, but then they found that offtake was low. They stopped it. Then later they found that power plant was really searching out for coal. Situation has not been very apt and very happy. But the fact remains that, I mean, since Dr. Srivastava told me that I must finish in 10, 12 minutes, so I will really cut short on all other things and welcome, in 2 minutes, welcome Gautam. We should be waiting for it. And but let me just tell you that this is placing a major challenge. But even if we are moving our power plants to the areas which are and the technologies and the processes which could be using the air processes, or they could be using water supply either from the sea or else from other plants, other municipal plants, so that the wastewater could be used instead of it, because water is going to be the next major problem, and that's again being looked into it. But whatever it might be, we are whatever the engineers might do, whatever the government may like, but it is not easy for India to move out of it. But at the same time, the disappointing results over the last 20 years, although one could say that the private sector put in only 0.69% into the R&D budget for the power sector, or it is basically for the overall sector, and public sector put in another about 1% or so. But then in future, we need to put in little more. It's not only just putting little more budget into it, but it is much more important that we have more coordinated effort onto a few technologies which are really going to really matter for the future. It is also necessary that we create an awareness in the policymakers about what needs to be done on the technological fronts, and also create an awareness of the capabilities of the engineers. And for that, engineers need to work also with other similar professional organizations, whether it's the management organizations or the financial organizations, to make sure that if we attain any breakthroughs, like you have seen that some of the startups have shown during last 18 months, and they're able to link with the financial institutions. If we are able to link with the financial institutions, then the future of technology acceptance would be much faster. And I'll just end that finance is important, but it is far more important that we have the competent people to do it, competent persons to take it forward. The institution has, over the last 2 years, where I was chairing the ICC, Bhaumik was chairing the CATE, and we have Dr. Srivastava and all other persons on it. We just find that if we did it in the right earnest, people did listen to us. In one of the webinars, we had more than 3,000 hooked on to the webinar, and there were many more following in the YouTube, etc. So we have to carry this message, keep the people's faith in the institution of engineers, and see what engineers can do in this field. And this MCDB is doing very well. I hope at the end of the day, Professor Bhaumik and all other experts will come out with these recommendations and present to the president, so that at the Engineering Congress in another 20 days, some of these recommendations can be taken up. Also give it to those eminent engineers who are delivering the memorial lectures, so they carry the message of this MCDB annual convention to the national and the international level. Thank you very much, Professor Srivastava, for your time. Thank you.
Thank you very much, Pradeep sir. As always, your words of wisdom have been a great asset for all of us at the institution and at this platform as well. You started with Glasgow Meet and shared PM's vision. I'm sure a lot of inputs have come through you only in that wisdom which PM has shared. Right? You talked about Panchamrit and differentiated between the net zero philosophy and the carbon neutral philosophy. We are focusing as a country on carbon neutral philosophy, and also talked about the importance of coal as a country for India. So thank you very much, sir. And with this, let me invite the chairman Debnath sir and Chinmay Debnath sir and Swapan sir to kindly take over the session. Swapan sir and Chinmay sir, please. Swapan sir. Moderators. Sir.
Chinmay is also not there.
Yeah. Kingshuk. Mr. Kingshuk, are you there?
Yes, sir, I am here.
Wonderful session. All the speakers were excellent, including and the chairman did a wonderful job. This is very good to see.
Right, then shall we conclude this session? Right. Thank you very much, one and all the panelists. Thank you very much. And we wind up this session. Thank you so much.
Thank you. Yeah, thank you, sir.
Thank you.
The chairman Kate is in another phone. I think he'll join soon.
Yeah. I believe we have concluded with this session. I'll request the organizers to kindly start the next session. Professor
Yes, sir.
Swapan, it seems, is busy. Right.
Yes, Papan
Thank
sir
you.
is phone.
Yeah,
Okay,
Mr.
sir.
Yeah, kindly start the next session. So thank you once again for all the speakers and the audience for this session.
Thank you, sir. Thank you, sir.
ঠিক আছে, এসে গেছি তুমি সব। স্যার,
Tell me.
ওকে,
Tell me.
হ্যাঁ স্যার, স্যার you have started. I was for the
No, I'm not
timing.
started. We are waiting for you to say the
Okay,
initial
okay.
words, then only we can start.
Okay, sir. Sir, it is audible, sir?
Yeah, it's perfectly fine.
Okay. So, good morning to all. I welcome again to everybody in our second day program of technical session 6, on the 36th National Convention of Mechanical Engineers and National Seminar on Innovations in Thermal Science and Engineering. During this technical session 6, we are having our Professor Gautam Biswas as a keynote speaker, as well as other two speakers we are having, Professor Pinakeshwar Mahanta, as well as Professor Rajat Gupta, and Engineer Tarun Malik will not be available. So to chair the session, upon this, we requested our Engineer Pradeep Chaturvedi to chair the session, because the Professor S.K. Kakoti was unable to join, so he has informed. So, and to help the Pradeep Chaturvedi sir, we are having the Professor Dr. Raja Chakraborty, Head and Associate Professor, Mechanical Engineering Department, TIT Agartala, and being a rapporteur, Dr. Shagnik Pal and Dr. Deepak Chandra Das will be assisting, those who are the Assistant Professor of Mechanical Engineering Department of NIT Agartala. So now I am handing over the microphone to our chairman of the session, Professor Engineer Pradeep Chaturvedi ji, to take the session, because regarding Pradeep Chaturvedi ji, nothing to tell. He is a man of energy and environment expert, and few times before he has been introduced by our Professor Aril Srivastava, so I am not introducing again. So over to Pradeep Chaturvedi sir.
Thank you. Thank you very much, Professor Bhaumik. I find that this convention has been going on very well. Yesterday you had very nice presentations, and the persons we have listed now to speak are really will make it an eminent thing. I don't know whether I just mentioned when I was finishing that you have an outcome of this conference and give it to the president immediately, so that before the Engineering Congress on 26th December in Delhi, they should use some of these as the inputs for, and maybe it can be given to some of the memorial lecture speakers. There are very many points which came out yesterday and this morning, and I'm sure these can be of use. Now, with these words, and thank you very much, Bhaumik, you and Devnath and all of you have done a wonderful job yesterday for doing all this. Is not so easy, and the support from the technical department. Now, we are starting with technical session 6. We are privileged to start with the keynote address by Professor Gautam Biswas. Although I'll formally, what is written down, I'll mention about him, but these words certainly do not really describe Professor Biswas or his eminence. He is far superior to what words would tell you. Professor Gautam Biswas is currently Professor of Mechanical Engineering at Indian Institute of Technology, Kanpur. He was the director of CSIR, CMERI, Central Mechanical Engineering Research Institute, Durgapur, before joining IIT Guwahati as director of Indian Institute of Technology, Guwahati. Professor Biswas was the occupant the position of GD and VM Mehta endowed chair professor of mechanical engineering at the Indian Institute of Technology, Kanpur. He was a Humboldt fellow in Germany in 1987-88, and JSPS invited fellow in Japan 1994. He is a fellow of the American Society of Mechanical Engineers. He has served a full term as the associate editor of the Journal of Heat Transfer of ASME. He was a guest professor at University of Erlangen-Nuremberg in 2002. He was the Dean of Academic Affairs at IIT Kanpur for 3 years since 2003. Professor Gautam Biswas is a fellow of all three major science academies of India, such as the Indian Science Academy, Indian Academy of Sciences, and National Academy of Sciences, India. He is also a fellow of the Indian National Academy of Engineering and the Institution of Engineers. He delivered prestigious Professor C.N.R. Rao Lecture in 2010. He has been awarded the STEAM J.C. Bose National Fellowship for the Department of Science and Technology, New Delhi, 2011. Wherever you will see on anything on engineering education, you look at any of the papers of the INAE for the last couple of years, you will find when you found only 3 names, Professor C.S. Jha, D.V. Singh, and Gautam Biswas. For a number of years, they have been at the helm of the affairs. And even for the Institution of Engineers, he is chairman of our division board for the publications. Gautam Biswas, I mean, I think whatever words I may use, but as I said earlier, he is one of the outstanding engineering academician, and it will be a great pleasure for us to listen to Gautam Biswas. Professor Gautam Biswas, please.
Professor Chaturvedi and all the colleagues, I'm really grateful to Professor Chaturvedi to introduce me in such an elegant manner. I do not know whether really I deserve that, but my heartfelt thanks to Professor Chaturvedi and Professor Bhaumik and all the organizers. Since you know that these days most of these online lectures are delivered recorded, so I yesterday recorded it and handed it over to Professor Bhaumik. So Professor Bhaumik and his team, they will play the record, and I will be together wherever needed. I will answer the questions, and after the lecture is delivered, I will be fully participating in the question answer session. So with my due regards and respect to all the organizers, and specifically Professor Bhaumik and Professor Chaturvedi, I would request the team of Professor Chaturvedi to play the, recorded. Yesterday I recorded and transferred it to Professor Bhaumik.
Okay, thank you very much. We'll start with that.
Good morning, everybody. I am really grateful to the organizers for inviting me to deliver this lecture. Respected Professor Kakoti, Professor Mohanto, Professor Bhaumik, Professor Chakraborty, Dr. Sengupta, and all the viewers. My today's topic is dynamics of vapor bubbles in film boiling with and without external electric field. Buoyancy-driven instability is the root cause of film boiling. Film boiling is a periodic phenomenon. Bubbles are released periodically from the nodes and antinodes. Vapor bubbles are placed on a square grid with a spacing equal to Taylor's most dangerous wavelength, and this is basically distance between two adjacent nodes or between two adjacent antinodes. And Taylor's most dangerous wavelength is given by twice pi root over 3 into sigma divided by rho L minus rho G into G, which can be also written as root 3 lambda C, where lambda C is the characteristics wavelength, which is given by twice pi root over sigma divided by rho L minus rho G into G. Rho L is the density of the liquid, rho G is the density of the gaseous phase, density of vapor, and this G is gravitational acceleration. So the Taylor's most dangerous wavelength is expressed by root 3 lambda C. We have used CLS VOF algorithm, coupled level set and volume of fluid algorithm for solving the governing differential equations and describe the solution for different situations. Now, void fraction is defined as F equal to rho minus rho G, density of gas, divided by rho L minus rho G. Now, void fraction advection equation is temporal derivative of F plus divergence of V into F equal to 0. Also in the domain, we define level set function, which is basically a sine function defined by a small quantity from the interface, small number, when phi 0 defines the interface, phi equal to plus d will be for one medium, say liquid, and minus d will be another medium, say vapor. The interface is represented by surface normal, which is grad phi divided by modulus of grad phi. Now, Young's method, which is also known as piecewise linear interface construction method, that is primarily used to calculate the surface normal at the interface for the cells that have interface. So surface normal at the interface and offset distance from the center of the cell to the interface. So N, which is surface normal, and the offset distance from the center of the cell, which is given by L, these two quantities basically identify the interface. And you can see, based on the void fraction of the neighboring cells, if Ij is the cell of interest, then the direction cosines and finally surface normal is calculated, and also the offset distance from the center of the cell is calculated. In order to make these piecewise line interfaces, to make them continuous, another procedure is adopted, which is called LVIRA, least square volume of interface reconstruction algorithm. Here, the estimated void fraction and actual void fraction is optimized when we are focused at one cell, 3 by 3 neighbors in 2D and 3 by 3 by 3 neighbors in 3D, and try to minimize this difference, which can be graphically represented as we have shown here, when this particular cell is the cell of interest and this dotted line is the basically interface between liquid and vapor, and when we calculate cell to cell, this quantity, this G function, is minimized in each cell by taking into account all 9 neighbors or all 8 neighbors. This cell is being the cell of interest, and similar way in each cell it is calculated. Now, level set function, as we have mentioned it earlier, this is a sine function. Its value is minus delta in the gaseous region, 0 at the interface, plus delta in liquid region, where delta is the shortest distance at a point R from the interface. Now, surface normal N and curvature kappa are recalculated from this mapped level set function, which is given by grad of phi divided by modulus of grad phi, and curvature value is minus divergence of n. Now, instead of minus delta, we substitute everywhere 0. Instead of plus delta, small quantity, we substitute everywhere 1, and this smoothness between 0 and 1 is established by Heaviside function given here by this expression. Then we use basically void fraction based density and void fraction based viscosity, and the interface, the surface tension force gets activated, and this is the way to calculate the surface tension force. Now, continuity equation in all liquid cells and all vapor cells are given by its usual form, divergence of velocity vector equal to 0. But for the two-phase cells, we take into account energy transfer and mass transfer. Basically, the energy that comes to the interface cell converts a part of liquid into vapor depending on the latent heat, and that is how the vapor mass is accounted for, and we use this modified continuity equation for the cells containing interface. That means for all two-phase cells. At the interface, we feel the presence of surface tension force. Surface tension force can have basically tangential component and also the normal component. Now, in absence of surface tension gradient, which is basically dependent on temperature gradient, here we encounter phase change phenomena. So interface is not a function of temperature. Interface stays at a specified temperature because of phase change. That is why the tangential component is neglected and we only take into account the normal component. So we can write the modified momentum equation as we have already mentioned, that here density is void fraction based density. Also viscosity is void fraction based viscosity. At the interface, we write the normal component of the surface tension force. As we have already mentioned, that tangential component of the surface tension force can be neglected since there is no variation of temperature along the interface. So the surface tension force, normal component of it, the normal force, is taken into account at the interface. It's also modulated by basically the delta Dirac function, which is only its presence is felt at the interface, and we also have additional volumetric electrical force term when we apply external electric field. Solution technique, we use staggered grid arrangement, which is basically similar to Mach algorithm. Grid spacing is uniform. Finite difference discretization scheme has been used. Second order accuracy is maintained throughout. Convective terms are discretized by essentially non-oscillatory scheme of Professor Stanley Osher. Convective terms are discretized by quick scheme of Leonard. Strong coupling between continuity and energy equation. We have already seen that form. Pressure equation is solved by an iterative method based on algebraic multigrid solver, HyPre. Then we test our algorithm for Stephan problem, and the velocity of this vapor front and the depth of this vapor zone as a function of time are validated through the comparison with the analytical solution, and we find the results satisfactory. Then we apply the algorithm for different interesting problems. The first simulation that is shown here is basically over a given space, identifying the basically regions of the bubble formation or the bubble formation sites. For Jacob number of 2.54, that means delta T, which is the indication of degree of superheat, we can see over this zone 6 bubbles, and the sites are separated by wavelength lambda, and this wavelength lambda is basically, we can clearly see, or if we calculate, we find out that these are √2 lambda c. Now, when we increase Jacob number, degree of superheat is increased from 2K to 6K. It remains almost same, but with the further increase, when Jacob number is 12.7, we see that these sites of bubble formation, they are separated by slightly longer wavelength. And at 14K, that means at Jacob number 17.78, we see that these bubble formation sites are separated by √3 lambda c. At 18K superheat, that means Jacob number 22.86, this is reconfirmed. Exactly the bubble formation sites are separated by a distance which is equal to the wavelength √3 lambda c. With the further increase of superheat, we can see here the bubble formation sites remain same, but instead of vapor bubbles, we observe the vapor columns shooting out from the sides. So these are basically indicative of formation of vapor columns. And this entire study indicates a transition from Rayleigh-Taylor instability, where the bubble formation sites are separated by √2 lambda c, that means the wavelengths are √2 lambda c, to Taylor-Helmholtz instability, where the bubble formation sites are separated by a wavelength which is √3 lambda c. So computationally, we come to the conclusion and we confirm transition from Rayleigh-Taylor instability to Taylor-Helmholtz instability. Here we reproduce some other results which are historically very important. These are the experimental results of Riemann and Grigul, where we can see the bubble formation sites, then alternate bubble formation sites become sites for vapor columns, and with the further increase in superheat, all the sites become the sites for vapor column formation. So here we can see this is alternate sites become the vapor column formation site, because if this is known and we can see vapor column formation, but at the antinode we can see the presence of bubbles similar to this. With the further increase in superheat, we can see it's not the vapor formation sites are not alternate sites. All the locations, all the bubble formation sites become the sites for vapor column formation. Vapor column formation at the nodes and antinodes. Now, this is typical evolution cycle. We can see the detachment of bubble at the node and alternately at the antinodes. When we superimpose electric field on a zone where the bubble formation is taking place, we include the effect of electric field, and this is basically called electrohydrodynamic model. In the absence of any time varying magnetic field, the curl of the electric field is 0. So curl of E is 0 and E is minus grad of psi, where psi is the electric potential function. The electric displacement vector, this is divergence of D equal to 0, where D is epsilon into epsilon naught into E. Epsilon naught is the absolute permittivity, and the electric field results in the electric body force, and this is a measure of electric body force, which is basically summation of Coulombic force due to free charge, then force due to gradient of electric permittivity plus dielectrophoretic and electrostrictive forces. So when we use pure dielectrics, basically in leaky dielectric it remains little complex, Coulombic forces are included, but for pure dielectric this volumetric charges are neglected, and for the body force term we can write basically the divergence of Maxwell's stress tensor, which is given by epsilon into epsilon naught minus half E square I. So we consider our fluid to be dielectric and we apply electric forces and see its effect on bubble dynamics. Next, we will consider effect of external electric field on saturated film boiling. Now, if we recall the variation of superheat and its effect on bubble formation, we can recapitulate that for 2K superheat we had 6 bubbles, 1, 2, 3, 4, 5, half and half, and the bubble formation sites are separated by root 2 lambda c. 5K superheat is also under Rayleigh-Taylor instability. And here also the bubble formation sites are separated by √2 lambda c, whereas for 18K we can see that no longer it is dictated by Rayleigh-Taylor instability. Now it is guided by Taylor-Helmholtz instability, and the bubble formation sites are separated by √3 lambda c. At a superheat of 22K, the distance between bubble formation sites remain same, but instead of vapor bubbles, vapor columns are formed. So this transition to Rayleigh-Taylor to Taylor-Helmholtz instability we have seen. Here we can specifically see that at lower superheat we can see discrete bubbles, smaller temporal frequency. This is the temporal variation, and as we can observe from here that this time period is for 2K, this time period is for 5K, this time period is for 18K. So the time period is reducing, means frequency is increasing. So basically at lower superheat, that means at 2K or 5K, we can see the smaller temporal frequency, larger time period, and larger time period together with higher peak of Nusselt number value. And for higher superheat, obviously higher temporal frequency, and at 22K vapor column are formed. Now for a given superheat, if we superimpose the external electric field, then we can see the effect of it. Here it is, to start with there is no electric field. Then electric field values are increased 1 into 10 power 4 volts per meter, 5 into 10 power 4 volts per meter, 1 into 10 power 5 volts per meter, and finally 2 into 10 power 5 volts per meter. So number of bubble formation sites increase with increasing electric field. Bubble release becomes aperiodic. In time, we can see with the higher values of electric field from periodic variation, it becomes aperiodic variation, and spatial periodicity is still maintained even at higher electric field and whatever superheat. Here it is relatively lower superheat. We can see the periodicity is maintained. Now, what we explained in the previous slide is animated here. So 5K superheat without electric field, 5K superheat with 1 into 10 power 5 volt per meter electric field, and 2 into 10 power 5 volt per meter electric field. Specifically here on this domain, we can see that at 40K superheat, without electric field, we can observe 3 bubbles, and with the application of 2 into 10 power 5 volt per meter electric field, we can see formation of 12 bubbles. Here we vary the electric field. We can see 0, then 1 into 10 power 5, 5 into 10 power 4, 3 different electric fields have been used. Maximum height of a bubble remains invariant with different values of applied electric field. Whereas radius of the bubble, we can see bubble radius decreases with increase in electric field intensity. Change in bubble profile is due to the combined influence of Maxwell stresses and the capillary forces. Now we can summarize. This is electrical influence number. This is T, delta T. So superheat, this is 2K superheat, 5K superheat, 10K, 15K, 18K. For every superheat, the electric field was varied. So electric influence number, that also varies. And for that, we get the value of enhanced heat flux with respect to heat flux at zero electric field. And these are Johnson's expressions. These are our calculations. And here, without electric field, of course, the experimental values of Berenson and the numerical values of Son and Dheer are compared with our Nusselt number values. These are our Nusselt number values without electric field and with electric field variation, without electric field and with electric field variation. Those are compared with Son and Dheer's results that are for without electric field, and of course Berenson's basic experiments. And as I said, this is the enhancement of heat transfer as compared to the heat transfer for without electric field or zero electric field intensity. Our calculations and Johnson's calculated values. Now we will look at reduced gravity in saturated film boiling. Reduced gravity, basically this increases length and time scale. We can see if gravity reduces, this is the length scale expression, characteristics length, root over sigma divided by rho L minus rho V. Rho V is the vapor density. We have used earlier rho G or rho V, they are same, into G, gravitational acceleration. With the reduced gravity, we can see that this is for G by G normal, that means normal gravity 1, the bubbles. Here for the reduced gravity, G by G normal 0.01, we can see much bigger size of the bubbles. And then if electric field is superimposed on it, we get back the normal gravity situation, or we even smaller bubbles can be obtained by applying 10 kilovolt electric field. These are results of Marco and Grassi, and here we can see basically comparison of interface profile, that means the bubble profile for normal gravity. These are given by red colored bubbles under normal gravity. You can see 1, 2, 3, half and half, 4 bubbles. Then at 0.37 gravity, we can see these green bubbles, and then 0.16 gravity, and we can see this blue colored bubbles. As we have already mentioned, that we are trying to mimic Mars gravity and the gravity of Moon, which is close to 0.1 of Earth's gravity. We have used a typical value 0.16, and we can see this is the temporal and spatial variation. Spatial variation we have mentioned, and time period for under normal gravity is 0.325 seconds, and for 0.37 gravity it is 0.95 seconds, and for 0.16 gravity, which is indicated by blue colored bigger bubbles, and time period is 1.95 seconds. So larger time period means a frequency is bubble formation is less. And the similar studies were repeated. These studies are for R134A with superheat of 20 K, and here water with superheat of 5 K. These are again repeated, and as usual the red colored bubbles under normal gravity and green colored bubbles are under 0.37 normal gravity, and the blue colored bubbles are at 0.16 normal gravity. And we can see the temporal variation also. Here it is 0.725 second at normal gravity, 0.37 normal gravity it is 1.8 second, and for 0.16 normal gravity it is 4.45 second. Now we can see here the number of bubbles formed at the same time interval are 5 compared to reduced gravity. This is 0.1 gravity, the bubble formation is taking place, and this is the maximum height reached by the bubble, very big bubble, and within this time interval already 5 bubbles have formed during this interval of time. So variation of apex height of bubble with time at normal and reduced gravity conditions for water at 5 K superheat. This shows variation of vertical velocity during the growth of bubble, that means bubble formation and finally detachment. This picture is for normal gravity and this picture is for reduced gravity. You can see bubble formation, then bubble detachment, and slowly the vapor recoiling force that brings back the residual vapor to the surface on the film, and that is why we can see this negative value of the vertical velocity. This is for reduced gravity and this is for normal gravity for R134A at a superheat of 30 K. Now this is comparison between heat flux variation with time at different levels of gravity for water at superheat of 5 K. This is basically average heat flux over the domain, and its temporal variation we can see with time, and for normal gravity, for 0.37 gravity, and for 0.16 gravity. And then we obtain the average values. So this is basically finally we get the space wise and time averaged values, and these are for normal gravity 66 kilowatt per meter square. For 0.37 gravity it is 42 kilowatt per meter square, and for 0.16 gravity it is 30 kilowatt per meter square, and for normal gravity it is 66 kilowatt per meter square. Similar numerical experiments are repeated with R134A with the superheat of 30 K, and here also we get the temporal variation of average heat flux, and this is periodic, and the average values are for normal gravity 28 kilowatt per meter square, for 0.37 gravity 19 kilowatt per meter square, and for 0.16 gravity it is 13 kilowatt per meter square. Now comparison of interface profile for a different instant of first set of bubble release for water with 18 K superheat, and at the normal gravity we can see green colored bubbles. Then at 0.1 gravity we can see basically this blue colored bubbles, and when we superimpose electric field on reduced gravity we get back this situation of bubble formation indicated by red colored bubbles. So we had 4 bubbles on this space for normal gravity. For reduced gravity, 0.1 gravity, we got this half and half blue colored bubbles. But when we superimpose electric field, we again get back 1, 2, 3, half and half, 4 bubbles with bigger size, but bubble formation sites are separated by again smaller distance like normal gravity. Here we do the similar variation with R134A, where the superheat is 20 K. This is for reduced gravity. For 1/6 gravity, this blue colored bubbles, 1, half and half. And then when we apply external electric field on it, and electric field intensity is 1 × 10⁵ volt per meter, we can see formation of 7 bubbles. This is a little more conclusive, where we under the normal gravity, with water with 18 K superheat, we observe the bubble formation sites and the bubbles. If we apply electric field of 2 × 10⁵ volt per meter on it, we can see the spatial frequency and temporal frequency both increase. Time period is basically 0.9 second, reduces to 0.235 seconds. Time period reduces means frequency increases. The bubble detachment or bubble formation frequency increases. Time period reduces, frequency increases. Similarly here, for the reduced gravity, for 0.1 gravity, we observe the bubble formation sites and bubble formation. When we apply again on this reduced gravity situation, that means 0.1 G, when we apply electric field 2 × 10⁵ volt, we see the bubble formation sites are separated by shorter distance, so spatial frequency increases and also the temporal frequency increases. We can see here time period is 3.8 second, and here the time period is 0.65 second. Time period reduces and temporal frequency increases. So what we narrated there, here we can see the animated situation, basically for normal gravity, and these are the bubble formation scenario for reduced gravity. And we can see the difference. These bubbles are having bigger size, these are having smaller size and already detached by the time it is fully grown. And then on normal gravity, we apply electric field of 2 × 10⁵ volt, and on reduced gravity, we apply electric field 2 × 10⁵ volt per meter. And again, we can see the bubble formation and the distribution of bubble formation sites and the bubble formation. Now, here we see the heat transfer characteristics for water at 5 K superheat for different values of applied electric field at the gravity level 1. This is gravity level 1, this is gravity level 0.37, and this is gravity level 0.16. And these are the variation of electric fields. Basically without electric field 5 × 10⁵ volt per meter, and then 8 × 10⁵ volt per meter. Here also same variation of electric field, and here also with 0.16 gravity, similar variation of electric field. Now we can summarize this variation. We can see gravity level 1, 0.37, 0.16, and this is the average heat transfer heat flux. This is 66 kilowatt per meter square, 42 kilowatt per meter square, 30 kilowatt per meter square. When we apply external electric field, then we see the enhanced heat flux and the percentage increase. Similarly, when we apply 8 into 10 power 4 volt per meter external electric field, we see the enhanced heat flux and the percentage increase. Now, the absolute value for 8 into 10 power 4 volt per meter is definitely very high for normal gravity level. But if we look at the percentage increase, then we will find at the reduced gravity level with the electric field intensity of 8 into 10 power 4 volt per meter, the percentage increase is 66.67%. So this is Q naught, this is QE for 5 into 10 power 4 volt per meter, and this is again enhanced heat flux for 8 into 10 power 4 volt per meter applied electric field, and the percentage increase is 66.67%. Now we go for a very interesting study. This profiles of bubbles at different instants of time. They can be collapsed on a single curve if we transform the coordinates properly. And here the z direction variation has been transformed into y star divided by t star alpha, and here the radial direction variation has been transformed into x star into t star beta, where the y star is basically z divided by lambda c by 2, x star is basically r divided by lambda c by 2, and t star is basically non-dimensional time. This time is basically t by TV, where TV is viscous time, L square by nu. So we can see with alpha and beta value, alpha 1.25 and beta value 0.5, the different variations, finally collapse on a single curve. And this is in the regime of Rayleigh-Taylor instability, where the superheat was 5K. A similar repetition of collapsing the dimensions and all the curves falling on a single curve happens even for under Taylor-Helmholtz instability condition. That means for higher superheat, for superheat of 10K, and similar transformation of coordinates, y star divided by t star into alpha, here x star into t star beta, and alpha and beta are different here, 6.4 and 4.5, but they sort of merge on a single curve, indicating the self-similar profile of the interface. So we can now conclude transition from Rayleigh-Taylor instability at lower wall superheat to Taylor-Helmholtz instability at higher wall superheat is justified. Increase in bubble density is observed over the domain with increasing electric field intensity. Bubble separation distance decreases with the application of electric field. The maximum bubble height is found to be almost invariant with the applied electric field. The lateral deformation in bubbles leads to decrease in bubble radius with increasing electric field values. With the reduction in gravity level, the length and time scales of the boiling phenomena increase substantially. The bubble size and height in reduced gravity level are much larger than those of the normal gravity level. The heat transfer rate is reduced as the gravity level decreases. The inclusion of electric field in reduced gravity scenario restores the value of heat flux commensurate with the normal gravity condition. The percentage change in heat flux due to imposed electric field is observed to increase with the reduction in gravity. The study of interface profile during the bubble growth showed that the bubble profiles at different instants of time tend to overlap with each other if a proper scaling law is defined for length and time. Thank you. Thank you very much for your interest.
Thank you very much, Professor Gautam Biswas, for your excellent presentation. Although we are over on time, but if there are some questions in the chat box and you'd like to answer, sir.
Yeah, I'm, I'll take any question.
Please.
But I don't find questions in the chat box. Maybe they can ask, directly.
If anyone has any question, they can ask directly. They have not put in the chat box. Professor Biswas has kindly agreed to respond. Anyone? Raise your hand and then ask. I think you have made a very elaborate presentation, Professor Biswas, and people are not coming forward with any.
I do not know. I know.
Maybe they have understood your work.
No, if any question, any discussion, any doubt, any sort of application related queries, anything is there, I'd be simply happy to interact.
In case we receive later, we'll forward to you, and you could take it up on the email. So.
Sure, obviously. But I believe that there are one or two groups in NIT Agartala. A few of them are associated with Professor Bhaumik also, some young faculty members. They are trying to work on free surface flows. I see their proposals in SCRB and several other places. So, such young PhD students or young colleagues, who are working with Professor Bhaumik and, other teams, if, they have any query, please, I would say, please come forward. Maybe people have little, inertia because of this remote connection and all, but it really doesn't matter. If there are questions, I'd be simply happy to interact. Or even, it need not be questions. It need not be, questions in the sense, sort of directly questioning the procedure or so. If somebody is having some suggestions, somebody is having some, sort of ideas, somebody, for all such things, I'll be simply happy to interact. As I said that, from these institutes like NIT Agartala, NIT Silchar, some of the NITs of Northeast, a good group of youngsters, they are doing free surface flow work and they are applying also for various projects. So if they come forward or try to interact, not only here, even later, I would be simply happy to interact.
Okay, Professor Gautam, since nothing is coming forward now, we'll keep it for a later date, and I'll ask Professor Bhaumik to send it across to you and then get in. Thank you very much. It was a great presentation that you have done, and we are really extremely grateful for your sparing your valuable time, Professor Gautam Biswas.
It's my pleasure. I can see you. I can see Professor Rajat Gupta. I can see Professor Bhaumik and Professor Devnath.
Wonderful presentation. Wonderful presentation. I was throughout there.
Thank you.
Thank you
so much.
Okay. Thank you, sir.
Thank you.
Okay. Now I'll request Dr. Rajat Gupta to come in and a brief presentation. Professor Gupta, a national scholarship holder and a PhD from IIT Delhi. Professor Gupta is 1959 born. He's a professor in the mechanical department of NIT Silchar since 1996. He was selected as the director of NIT Srinagar, Jammu Kashmir in 2011, successfully completed his 5-year tenure. Thereafter, he joined back at NIT Silchar and he was appointed by MHRD there as the officiating director of NIT Silchar in July 2017. He joined as the director of NIT Mizoram, which is one of the 10 new NITs established in 2010. He has published more than 180 research papers in various national, international journals, conferences, and written many books. He has produced many PhDs and MTechs. His research areas include, among others, fluid mechanics, CFD, non-conventional energy, thermodynamics, etc. He chaired various national, international conferences and delivered keynote addresses and associated with various committees of MOE, Government of India, NBA, AICT, NIF, Ahmedabad, IEI, ASME, etc. He was the founder chairman of Mizoram State Center, the Institution of Engineers. Seen many awards like Education Leadership Awards, Rajiv Gandhi Education Excellence Awards, etc. So, Professor Gupta, over to you. And I've been told by organizers that your and Professor Mohanto's presentations are to be finished before 1:30. So you manage your time yourself. How much?
Thank you. Thank you.
Yeah.
Thank you.
Because they said that is
Namaskar.
where the system may go out. So that
Yes. Thank you for your nice words about me. And it's always a pleasure to meet you, to have discussions with you. I have learned many things from you.
Thank you.
At the very outset, I express my gratitude to Professor Bhomik, the chairman Kate, and Engineer Chinmay Devnath, the chairman of Tripura State Center of Engineers, for giving me a chance to say something about my research topics. I thought of discussing something which my students did at NIT Silchar. That is, we all talk about the conventional energies, but I'll be talking something about the renewable energy and how that, especially in the Northeast, that energy is a big issue, and how that wind energy can be utilized to generate power. Now, we know that in the coastal zones, that a lot of horizontal type of wind turbines are there, and a lot of power is generated to this. But what about the low wind speed? Can you generate some power utilizing the low wind speed so that at least the remote places and rural places, the electrification is done, or maybe say irrigation or household works are carried out. So this is the purpose of the whole research work. Here, what I'll do is that basically there is a net problem. So I'll keep my video off and I'll share my presentation. And at the end of the presentation, I'll keep my video on. So basically what I decided is that this is intended to the research scholars and the young faculty members. I'll talk about the vertical axis wind turbines, how the vertical axis wind turbines can be developed, and how the performance can be improved upon. And you know that the wind velocity in the northeast zone is low, then there is hardly any study regarding the wind velocity. So I'll just discuss about the wind velocity distribution at Silchar as well as at Agartala, because both the places I'm associated with. That's what my presentation all about. So now I'll share my slide, keeping my video off. আমার একটা প্রেজেন্টেশন আছে আলাদা allow me for screen sharing.
Sir, kindly share your screen, sir.
Yeah. I'm trying. Allow me.
Yes, sir. I have already given the access, sir.
Okay. Till disabled. Till disabled.
Okay, sir. I am trying my.
Please do it.
Sir, now.
Let me try. We're getting.
Yes, sir. Yes, sir. It is coming. Thank you, sir.
So as I mentioned, is that I'll be talking about some research works conducted by my students. So basically, these are the what I'll be presenting is basically the works done by my students who are faculty members in different organizations now. So this is all about that the global final energy consumption. This slide I'm showing. This is your M2. M2 is nothing but megatons of oil equivalent. The unit quantities, the amount of energy released when burning 1 megatons of crude oil. And this is your height. And you see current global energy scenario. When you talk about the wind energy scenario, then India is about 5% of the total installation onshore, and offshore there is hardly any. These are all the data collected from this. Now let me see how a wind turbine extracts energy from the moving air by slowing the wind down and transforming this energy into a spinning shaft, which usually turns a generator to produce electricity. The power in the wind that's available for harvest depends on both the wind speed and the area that's swept with the turbine blades. So these are the, you can see this diagram, size of the wind turbines, the small, less than equal to 10 kilowatt, you can say small. Yes, this, as I mentioned, that is utilizing that wind speed. So this can be utilized for water pumping, then telecom set, or in remote places. Yes, India is a huge country, and yet electrification is a big issue till now, although government is trying to make 100% electrification. Nevertheless, this is also required. Now, intermediate is your 10 to 250 kilowatt, the village power, hybrid systems, and distributed power, and large, something like that, 250 kilowatt to 2 megawatt. Difference. This is the horizontal axis turbine. As I mentioned, this is mostly used in the coastal zones you have seen. And these are the vertical axis wind turbines. You can say animation I'm showing. The figure A is showing the conventional Sibelius rotor. Figure B is showing the Darius rotor. H is showing that. Figure C is showing that H Darius rotor. And D is the hybrid rotor. Now, power coefficient graphs for various wind turbines. This slide we are showing. This is before the NACA. When you talk about the profiles, you see that wind turbines here, Sibelius type, Darius type, edge type. These are all talking about the blade. This H, it is H type. This is a meaning as S type of thing. This is egg better type. That's what it is called radius type. So this is like something like that egg better type. You see the egg better. You have seen this one. This is so similarly. You can talk about the NACA profile, that National Advisory Committee for Aerodynamics. This is the NASA. The major contribution of this agency includes NACA. Now, the NACA airfoils are airfoil shapes for aircraft wings developed by NACA. The shape of any NACA airfoil is described using a series of digits after the word NACA. Example, NACA 2415. It means that this airfoil has a maximum chamber of 2% located 40% from the leading edge with a maximum thickness of 15% of the chord. I'll show you by showing the diagram also. This is the diagram is showing that, you know, that this is the symmetrical one. This is the chord, this is symmetrical airfoil, and this is the unsymmetrical one. This is this mean chamber line and the chord line. You can distinguish between this, and here your chord line and mid chamber line coincides this one. So this is the NACA profile. As I mentioned, that NACA 4-digit, the 4-digit 4412. This 4412, the first for the maximum chamber in percentage of chord, 4 position of maximum chamber in 1/10, this one, and this maximum thickness in percentage of the chord. So this is this NACA 0015. Basically, it's a symmetrical airfoil, and this NACA the 2415 is this unsymmetrical airfoil. So these are the basic parameters of the wind turbine. As I mentioned in my opening remarks, this is basically the works conducted by my students, and this is mainly intended to the research scholars and the young faculty members who are working, and if they're interested to do some research work. That's why I'm giving all the details here. So I prepared a lot of slides. We're sharing this very fast because of the paucity of time. Later on, you have any questions, my email ID is given, my mobile number is given. But this slides, I prepared a lot of slides so that these slides will be very much useful to you if you are really interested in this one. So pictorial representation for the basic parameters of wind turbines. This is the pictorial representation. I'm showing the governing equation for wind turbine modeling. Here, I'd like to mention is that one should have a sound knowledge about the fluid mechanics while doing this work. So now these governing equations, Navier-Stokes equations, which are suitable for wind turbine modeling, is responsible for this. And this aerodynamic methods of solving this research problem, there are basically two ways by which you can resolve or solve this problem. One is by theoretical method, another by experimental method. Here, exactly what I want to mention here is that I'll be showing some results which are conducted experimentally, and I'll be showing some results which are conducted computationally. Then the results were compared. Then I'll show that the basic approach now, this is computationally, that computational fluid dynamics is one of the branches of fluid mechanics that uses numerical methods and algorithms to solve and analyze problems that involve fluid flow. Basic approach to using CFD basically is a pre-processor establishing the model. Now, identify the process and equipment to be evaluated, represent the geometry of the interest using CAD tools, use the CAD representation to create a volume flow domain around the equipment containing the critical flow phenomena, create a computational mesh in the flow domain. Now, this is the pre-processor. Now, next part is the solver. Identify and apply conditions at the domain boundary. solve the governing equations. As I mentioned, that governing equations, you have to solve the governing equations on the computational mesh using analysis software, and then the post-processing, that is the interpreting the results. That post-process process the completed solutions to highlight the findings, interpret the prediction to determine design interactions or possible solutions if needed. Now, the governing equations, as I mentioned, in the CB is the continuity equation, momentum equation, and energy equation. I'm not going the details of these things, and all the things are depicted here. Now, the turbulence model, the choice of turbulence model will depend on considerations such as the physics encompassed in the flow, the established practice for a specified class of problems, the level of accuracy required, the available computational resources, and the amount of time available for the simulation. Now, the participants, those who are research scholars and the young faculty members, I want to address here to you is that what I've written here, this choice of turbulence model will depend on considerations such as the physics encompassed in the flow, the established practice for a specific class of problem, the level of accuracy required, the available computational resources, and the amount of time available for the simulation. So these are various solutions, one equation model, models, Kaplan models I mentioned, and depending upon this, you have to select this one. Selection also required knowledge of it. Now, advantages of CFD, you know, that is, it provides the flexibility to change design parameters without any problem. Advantages of CFD, that it provides the flexibility to change design parameters without the expense of hardware changes. Now, in the experimentation, you cannot change the things as you wish. Once you make the models, you have to conduct the experiments and you have to make a new model to make the new experimentation. But this is not required in case of CFD. So when you find that, yes, you have to change the model, what you have to do, you have to change the model immediately without any expenses, only some time is required. So this is a great advantage. And moreover, for experimentation, you need the experimental setup. This experimental setup may not be available in many of the institutions or organizations. So this is very fast, and it guides the engineer to the root of the problem and is therefore well suited for troubleshooting. But here I want to give a caution to all of you, in the sense that those who are interested in work, that there is no substitute for experimentation. I'll talk about this. Design and fabrication of the models. The best part is that you do the let us do the experimentation and compare this with our computational work. That is the best possible way of doing the thing, exactly what we did there. So design and fabrication of the models, I'll be showing some models here. So two different blade materials, the lightweight aluminum and fiberglass reinforced plastic, FRP. FRP used was a composite of the PVC type thermoplastic. Here I'll be showing the models, and you see these are the models. This is 2 buckets of an rotor. 2 bucket means this is the 2 bucket. 2 buckets. This is the 2 one. This is 1 and this is 2. 2 buckets of an rotor. This is the 3 buckets of an rotor. 1, 2, 3. 1, 2, 3. 3 buckets of an rotor. Now here, combined 2-bladed Savigny's Darius rotor. I showed you the Darius rotor. Here, this is a combined. This is the Darius is at the bottom and Savigny's at the top. this is combined, this made, and this is the combined two-bladed Darius Sabinius rotor. This is two-bladed Darius Sabinius rotor. This is made is Sabinius is bottom and Darius at the top. Combined three-bladed Sabinius Darius rotors. This is 1, 2, 3, and this is your Sabinius, and this is Darius. Both are of three-bladed rotors, and it's combined. This one, you see this one, and the reverse is that combined three-bladed Darius rotor. Here in this case, Darius is on the top and this Sabinius at the bottom. So these are the two-stage. Now here the two-stage Sabinius. Earlier what I showed you is the one stage only. Means this is one stage. This is one stage. You can see this is one stage. This is stage. But here what I'm showing is that two-stage, two-bucket Sabinius rotor. Two-stage, two-bucket Sabinius rotor at 90-degree phase difference. So these are the models prepared by my students, and they conducted these tests. Now, as I told you, that methodology of doing the either experimentally it can be done, or it can be done computationally, or it can be done both. Here he did both. Now, wind tunnel. This is the wind tunnel basically that that was available at NIT Silchar. This was installed in 96. This wind tunnel in the Department of Applied Mechanics. Now, this is, you know that there are various types of wind tunnels. So this is a subsonic wind tunnel. And this wind tunnel was constructed in association with IIT Delhi. Because getting a wind tunnel properly manufactured was a big issue in that year of 90s I'm talking about, because you know that accuracy was an issue. Then I tied up with IIT Delhi, and today I express my gratitude to my guide, Professor Sheshadri, who is in Mysore now. Recently, I went there, I met him. I express my gratitude all the time. What I am today, because of Sir and my another guide, Professor Hasan Singh. So I take this opportunity to express my gratitude to them. And because of them only, that NIT Silchar, at that time it was REC, and when we are REC, we are very poor actually. You know that when state government Agartala Engineering College and now NIT, you could see the difference between State Engineering College Agartala and the NIT. Similarly, our is also like that. At that time, you were REC, and now we became NIT only in 2002 onwards, and then only funds started flowing. Earlier, getting wind tunnel and making the wind tunnel, spending money was a big issue. Anyway, then Principal Professor Borbhaiya sir had faith in me, and he gave me the full liberty to tie up with IIT Delhi, and accordingly IIT Delhi people came to REC Silchar and constructed the wind tunnel here, and then they installed that. Why I'm telling so many things here is that where there is a will, there is a way. That exactly I want to say. That at that time I thought that yes, we don't have anything of the winter is required very much, but we cannot purchase this. Then like this Professor Bhomik, he is making tie-up with so many distinguished professors across the globe. He has a wonderful quality, and you know that yesterday there are 4 professors from abroad presented the papers. Similarly, this morning also that Professor Bhomik and Professor Chinmay Devnath, Engineer Chinmay Devnath, they have utilized their resources to rope in the best in the country and in the world to deliver lectures. during this today convention and national conference. So that is the capacity they have. I do not equate this, but what I want to say is that sometimes we, the teachers, I'm addressing to the that young teachers. Sometimes we say that we don't have this, we do not have this. How can you do like this? And we lodge complaints so many times. So basically, we engineers are the problem solvers, not the problem creators. This is the background I said that the wind tunnel, basically I'm talking about here is that subsonic wind tunnel. Now this is the this is the test section. This is the test section, and here the model is installed. Then you conduct the experiment through this. So I'm showing this. Now, these are some of the results. Two-bladed airfoil edge radius turbine having blades. This is some of the results. I got it. So this now just one or two results I'll just show you here. This is that H by D ratio, CP, that coefficient of performance. So CP of H radius turbine increases with the increase of the H by D ratio up to a certain limit. After that, it decreases. CP of airfoil core two-bladed H radius turbine is higher than three-bladed H radius turbine. The highest CP of the FRP of two-bladed is 0.267, whereas for aluminum blade it is 0.237. That is FRP, the CP is higher. Now, this power coefficient of H radius rotor increases with the increase of the H by D ratio up to a certain extent, but then decreases with the further increase of the H by D ratio. The power coefficients for both two-bladed airfoil core, H radius, turbine or aluminum FRP blade material are higher than those for three-bladed airfoil core H radius turbine. The optimum H by D ratio at the highest power coefficients for the two-bladed and the three-bladed turbines of aluminum or FRP blade material are the same. The two-bladed airfoil core H radius turbine having FRP blades produce the highest power coefficient of 0.267. Among all the areas. I'm talking about this. Now, this is the CFD analysis, this pre-processing, as I mentioned earlier, then the solver is using the Fluent. These are the results, and that solving by this, I'm showing the matching of this. The percentage deviation of computational CP from the experimental CP is around, you see, that plus minus 3.12%. So there is a good match between the computational. Similarly, for this case also, CT case also, the percentage deviation is 1.15%. Here in this case, the percentage deviation is further less. So what is to be concluded is that there's a good match between the computational and the experimental work. Now, some more that selection and fabrication of the edge rotors for experimental setup. Now, in why I have selected this, there is a reason for selecting this work. This is another work done by another PhD student. Now, at that time, the wind tunnel, which was there, which was installed in 1970, became non-functional. I'm talking about the year 2009-10, something like that. It was. I'm talking about that year, 8, 9, 10. That become non-functional in the sense that because lot of works conducted in the wind tunnel, and finally that it got this. There is a shelf life for all equipment. Similarly, here also that wind tunnel had a shelf life, and then in 2009-10, that was not functional properly. But again, you know that again, as I said, that where there is a will, there is a way. That we did not have the wind, we did not use the wind tunnel for conducting our experiments. But what we did is that you see this blower. So the centrifugal blower apparatus, we have this thermal lab. In the thermal lab, what we did, we utilized this blower case, this blower. And this blower is the coupling. I'm showing you flow rate, control valve, all this thing I'm showing. And the exit of the blower, we kept this, our models. Our model was kept here. So you see the model, this one. So my dear participants, what I want to emphasize, why I have selected these two. One is that when all the things are available with you, we conduct the experiments and this. And the second case, what I'm showing is that the apparatus, the equipment was not available. The experimental setup was not available. Wind tunnel was not functional at that time. Can you think of something else? Exactly, we thought that if wind tunnel is not there, how does it matter? Let's see, can you do something utilizing the blower facing? And basically we need this one, and we did one. And you know that this he has published 5 SCI journal papers, 5 SCI journal papers based on this work. So that's what exactly I wanted to emphasize, my dear participants, that sometimes something may not be available, but be innovative and do something. This is the theme of this national conference, is also that innovative thermal sciences. Now, these are the models. I'm not going into details of this. That is the schematic diagram of the whole experimental setup. That was made. This model. This is. Now, this is the different equations used and the results we got. And there is here also that we did this computational analysis using the CFD. And this is the matching between the computational and experimental setup is, experimental is quite good. And this is that now that I'll show you something about the wind data. Because as my opening remark, I said that in the coastal zones, the wind velocity are very high, and there is a lot of horizontal types of wind turbines are installed. But we are interested about the low wind speed, and I belong to Northeast, and then I tried to understand that how we can do something here also. So, but hardly there was any data available, and very few people could do something about this wind analysis part. So what we did is that we collected data for 5 years, 2003 to 2007. This is the work of my student, then of Silchar zone, because I belong to Silchar. I did similarly for Agartala also. So we utilized 2 methods. This is a statistical method, Weibull method, and Rayleigh's method. Now, finally, what I want to say is that I'm not going into details because of paucity of time. Now, this particular site is not ideal. This particular site, in the sense of Silchar site, is not ideal for grid-connected applications, since wind energy density is less than 100. However, this level of wind energy density would be adequate to stand-alone applications such as battery charging and water pumping. So that was our purpose, basically. Similarly, you see, this is the Agartala region. This is the data Agartala region from 2009 to 2013 of 13. So this is another student did this work. Here also the wind velocity is more or less like Silchar only. Silchar only, not suitable for this one. Agartala, this not suitable like Silchar also, as I mentioned that. But it is very much useful to generate small power for small applications like charging and water pumping. That is the purpose of this study. And you know that there is hardly any difference of the pattern of wind. So whatever the study conducted in 2003 or 7 or 9 and 13, 2021 and 22, same thing more or less will hold good here. That is okay. Now, here I'll give you some future scope quickly I'll give you for some future scope for the wind energy. Darius rotor being a lift-driven turbine faces a dead band region initially, and overcoming it becomes challenging. What is the challenging in the vertical axis wind turbine is that the efficiency of the vertical wind turbine is very, very less. You know that maximum efficiency we can go up to 59%. Now the horizontal axis wind turbine efficiencies are quite high, but in the vertical axis wind turbine the efficiencies are very less in the range of say 15%, 18%, 20%, 22%. So if we can increase the efficiency, how to increase the efficiency? That is the whole purpose of doing the things as we are talking about the different types of size and shapes of the blades, and including the aerofoils and this one. So that is the whole purpose, and this doing these things with the fluid mechanics behind this. I'm not going all the details of nitty-gritties of this, but again, you see that if we can increase the efficiency in this CP of the turbine, that is our purpose is fulfilled. Now, some of the applications of the vertical axis wind turbines I just mentioned here is that wind power generation mainly includes grid-connected and off-grid wind power generation. The large-scale wind turbine is often used for grid-connected power generation. The middle and small-scale wind turbines are usually for off-grid power generation. Electrical power generation, it is usually used in the power supply of steel pump and home lighting, etc. Because the wind in nature is not stable, the wind energy is often used together with other kinds of renewable energies such as solar energy, biomass energy, water energy. Is called hybrid type of thing. This type of energy system is called hybrid energy system. Now, there are many other applications of vertical axis wind turbine except electrical power generation. From the point of energy conversion, wind power can be transformed to mechanical energy and heat energy. Therefore, that vertical axis wind turbines energy system can also be used for water pumping, heating, and cooling. Windmills have been used for centuries to pump water, and Green Asians used wind power to lift water for growing crops, while Europeans have used windmills to pump water into the sea so that land. So vertical axis micro wind turbines are being installed in home-built environment to satisfy the people's energy needs. That is the build. There's many places at the top of the roof that vertical axis wind turbines are installed, and that small power is generated. So this is very rampant now. In India also it is coming up in a huge way. So finally, I conclude by saying that the very purpose of this presentation is that I showed some results of my students here, and I prepared some slides collected from them only. I compiled with the help of my MTech student, Mr. Dubey, who is sitting in front of me right now. Now, the whole purpose of making this is that the participants, research scholars or MTech students or young faculty members, those who are working in the research, if they're interested to do something about wind turbine, especially in the vertical axis wind turbine, and if they want any assistance from my side, that yes, now we have at NIT Silchar, we have the wind tunnel also, so they can I am always ready. I am always ready to help you for this, and I thank you once again, Dr. Chaturvedi, and the organizers of this for giving me an opportunity to say something about my research work. I thank my students and I thank my MTech student, Mr. Dubey, for helping me for preparation of this slides. Yeah.
Thank you very much, Dr. Gupta. You made an excellent presentation, especially differentiating, identifying what sites can be useful for the grid connection. I mean, not many studies have been done, and I'm sure the government will, and the implementation agencies will take care of it. Northeast is anyhow being identified as important source for the wind mills, and locating windmills for small sizes and large sizes will become important. And our whole difficulty is the grid connectivity and identifying what loads in the grids will be coming in and coming out, going out, and how they will happen. And I'm sure many modifications on your studies or additions, subtractions may be done, but it's a wonderful thing. So now you have really made a very exhaustive presentation. And if you permit me, I'll request the next, because we already overshot time.
Yeah. Okay. I have got another meeting also.
Professor Chaturvedi, just if I can ask one very short question.
Please go ahead. Go ahead.
Professor Gupta, it's a very nice presentation with very elaborate work done, and I hope that it continues. My only suggestion would be, are you in touch with any power electronics people in NIT Silchar?
Not yet, sir. Not yet, sir.
So this grid connectivity and balancing the grid, basically when you will be pushing power from the localized sources, and when the local distribution will draw power from grid, this control is very important for all such initiatives. And I have a very modest request. If you can if you can integrate a power electronics person from your electrical department,
I'll do, sir. I'll do. Definitely.
It will be wonderful. Thank you.
Definitely, sir. I'll do, sir. Electrons people, there is a meeting now at 1:30. I'll tell your suggestion there, sir. The golden.
Typically not the electronics people. These are power electronics people who are electrical people.
Yeah.
Right. Electrical people, quite often they contribute to grid balancing and localized, grid connectivity. So people who are in power electronics, such people will be able to really put you on right perspective. Thank you. Okay. I'll not take any.
Thank you. Thank you.
What Dr. Gautam Biswas has said is a very critical issue, and everyone who is working on to the grids are finding out the power electronics required for grid connectivity and going off the grid is a very important thing. If you can come out with a combined model, that will be very useful.
I'll try to do it. Is it one of the suggestions?
Yeah.
Okay. Thank you very much.
Thank you very much.
Okay. May I leave?
Yeah. Thank you very much. Now I have great privilege in inviting Professor Dr. P. Mahanta, Professor, Department of Mechanical Engineering and Director, National Institute of Technology, Arunachal Pradesh. Professor Mahanta obtained his PhD degree from Department of Mechanical Engineering, IIT Guwahati in 2001, and soon after joined the department as assistant professor and eventually was promoted to professor in April 2008. He held numerous administrative positions within as well as outside the institute over the years, as head of Center for Energy, as head of the Department of Mechanical Engineering and Dean of Faculty Affairs, as officiating director IIT Bhagalpur, and currently as director of NIT in Arunachal Pradesh. His major areas sponsored research from various funding agencies, 3 of which are recent projects funded by ESPRC UK, European Commission and Research Council UK. Professor P. Mahanta have established an international platform for research in the area of bioenergy with University of Nottingham, University of Birmingham, and Loughborough University, UK. Similarly, he has He established collaboration in the field of clean coal technology with University of Cranfield, UK, and UCL, Belgium. So far, 25 students have been awarded PhD under his guidance. He has jointly mentored a visiting fellow from Zimbabwe under the C.V. Raman International Fellowship and African Researchers 2010, DST Ministry of Science and Technology, GOI, for a period of 3 months. He has also been involved with national level extension activities like development of course materials for NPTEL web course and have also developed course material for IGNOU. He has jointly organized several short-term courses, summer schools, and winter academy. So he's also involved as an active member of the various technical and scientific committees such as BIS, Regional Science Society, etc. He has received the Indian Distinguished Visiting Fellowship from University of Nottingham for the period of 10/6 to 2010. He has published a number of papers and written chapters for the books. He is a fellow of the Institution of Engineers and ISTA Society, Japan. I have great pleasure inviting him. Before I request him to make his presentation, I'll have to offer my apologies because at 1:30 we have a very important meeting with the Delhi State Center. We are doing the Engineering Congress and the Finance Committee has to meet to approve certain things. I'll log off at 1:30 to be a part there to get the necessary funding approved. And I'm sure Professor Malik will then will take over and then he'll.
Okay, sir.
Thank you. So please go ahead, Dr. Mohanta.
Thank you.
Yeah.
Thank you, Professor Chaturvedi.
Yeah.
How much time I'll get? It
Half
is
an hour.
1:27.
I was told that half an hour is being given to everyone.
Okay. Thank you.
But if you can economize is okay, but half an hour was what was slated. Go ahead.
Okay. Thank you. Thank you. So, Professor Chaturvedi, Professor Bhaumik, Professor Biswas, Professor Rajat Gupta, other participants, reporters, and other moderators. I'm very happy that I have been invited to give this particular talk. Actually, I'll be talking about some issues involved with renewable energy application for energy sector in Northeast region and India as a whole. And also, I'll indicate time to time about the innovations that can be carried out or that can be done at done by the researchers as well as practicing engineers in a field of renewable energy. So as we know, more than 93% of this primary energy is obtained from conventional fossil fuels like oil, gas, and coal. Out of that, 75% of the India's electricity is achieved through coal thermal power plant only. If we consider China, it is almost 75% coal is used. In USA, it is more than 40%. Japan, it is 32%. And if you take Germany, it is 38%. But this fossil fuel has very high cost and the cost is increasing monotonically. Second important issue with the fossil fuel is the quality of fuel. Particularly if we take coal as the primary fuel for power production, it has got very high ash content. That is one of the problems. Then coal contains 1 to 3% sulfur in India, and there is also particulate emission. These three issues are always encountered when coal is used in the power plant. And India's total, out of this power produced, total carbon dioxide that is emitted in 2020 was 2.63 billion tons, out of which 64% is contributed by coal combustion only. So environmental pollution, including greenhouse gas emission and acid rain, are major factors why use of coal is discouraged. But we have an ample reserve of coal, which will last more than 111 years. So there should be some mechanism to use coal for or some strategies so that we can go ahead with improved technology with coal, as well as some alternative energy sources. That is why this renewable energy is coming into picture. So total energy generation capacity in the country in the year 2021 is 390.8 gigawatt, whereas we require 4 trillion units if we propose growth rate of 10% annually is 4 trillion units. Out of that, you can see I have given 73% is from coal, 4% is from nuclear, 12% is from hydro. Then biomass is playing a very minutiae role of 1% only. So overall, you can see that Indian scenario says that coal has to be used, but it gives a lot of problem with carbon dioxide emission and greenhouse gas emission, and NOx is another issue. Then coming back to Northeast region, the coal share for power production is 38%. Gas used for power production is 36%. Gas produced is 38%. The coal share is 17%. The diesel is also used some purposes, that is almost 2 to 3% now. Hydro contributes 36%, and remaining renewable energy sources, that is 8% now. So growth rate of renewable is slightly increasing day to day. So the constraint in energy generation in India as a whole is that the conventional power generation with fossil fuel is one of the major constraints. So that gives birth to loss of efficiency, and second important issue is the greenhouse gas emission. Second issue is replacement of these power plants. Replacement of these power plants with clean coal technology is not financially viable. Third important issue is shifting completely to renewables quickly is not possible due to the various constraints that will come to that slide later on. Then thermal and electrical storage technology at large scale is financially and technologically cost intensive. India also have to match with the world's requirement, that is global issues like greenhouse gas. In Prime Minister's Committee of Parties meeting in Glasgow recently, it was been framed that India will meet 50% of its energy requirement from renewable energy by 2030. And by 2070, India will achieve the target of net zero carbon. So to take the solutions, technological options are to go for combined cycle power plant to increase the efficiency, co-generation units, IGCC, that kind of modern technologies. Then integration of different power plants to grid. Then integration of renewable energy to the conventional power plant. Use of biomass with coal in coal-fired power plant, and gradually increase the share of renewable in total power generation. That is the domain of achieving sustainability in energy development in India. Now, if you go for Northeast region, hydro has a potential of about 58,971 megawatt, including big, small, and mini and micro hydro projects. Solar has the potential of more than 60 gigawatt of power production. If you see this figure, for each of the state, the figures given are in terms of gigawatt. Like Arunachal Pradesh, potentiality is with solar is 9 gigawatt. Assam is having a potentiality of 14 gigawatt of power production, and so on. Biomass is having potential of 750 million metric tons of biomass available. Out of that, India can have biogas production of 29 to 48 billion meter cube per year, and it can also give a slurry or manure up to 350 million tons from 980 million tons of cattle dung available annually. Wind power at two different heights, 50 meter and 80 meter, and combination of that has the potential of only 810 megawatts. Both Mizoram and Tripura do not have as such potential in terms of this 810 megawatt. Our survey is very much limited. As Professor Gupta has shown, if wind power is there also in Tripura and Mizoram, that figure is very insensitive and very low. Only it can be used as a standalone unit. For grid connectivities, this system cannot operate. So wind potential has to be validated for all the states in Northeast with proper measurements. Then for solar energy, already we have the different installed capacity I have shown here. And most of the applications are like heating of water, solar thermal station, photovoltaic panels, etc. Now, these solar applications, you can see the plants are usually in barren lands, low maintenance is required, top surface cleaning is needed because of a lot of dust, long life of PV panel is there, but because of the dusting and lack of maintenance, the panel life decreases. Then solar PV can be isolated as well as grid connected. I'll show some of the applications of solar energy. This is in IIT Guwahati itself. It is a 500 kilowatt peak power production at the rooftop of IIT Guwahati's library building as well as one of the hostels. Then this is another picture having a 1000 kilowatt peak capacity at rooftop grid connected solar PV, but this is standalone. We do not have grid connectivity. Apart from that, all of the major institutions are invited by Ministry of New and Renewable Energy to go for using solar standalone as well as grid connected solar power production. So many institutes have taken this, the module of 500 and 1000 kilowatts so far. Regarding application, other thermal applications, hot water production is one of the important issues, like food processing, parboiling of rice. It is in Tripura and Bangladesh, it is very common. So for that, you require hot water at 70 degrees Celsius. The paddy has to be soaked for 7 to 8 hours. So a lot of heat is required. So that kind of heat can be taken from this hot water production from solar. Then anti-termite treatment of agricultural products. This can be used from hot water production from solar. This is an established technology. Hardly any maintenance is required for this type of panels except removal of dirt, and long period of utilization can be achieved. These are some advanced technologies like in Rajasthan, 50 megawatt solar power plant has been already been installed. This is a heliostatic power plant in Israel. So they produce directly, convert like a conventional power plant and replace the conventional power plant. So it can be used for boiler operation and power production directly, power for milling, threshing, power for run small processing units, and as a whole for generating electricity. This is one of the innovations I'll mention. Innovation is required in this field, particularly drying. So solar drying, hot air or hot water drying. Many types of solar dryers are in research and some prototypes are made and few companies have come up, but efficiency of these dryers are very poor. And in the Northeast particularly, we have some specific crop, like in Arunachal Pradesh, we have big cardamoms that is grown. Then we have kiwi fruit. Drying of those fruits are very difficult. For that, we require some innovation. Even though we directly use a conventional dryer, the drying capacity of this type of fruits doesn't meet the purpose. As for example, for kiwi drying, we require relatively low temperature and long time for heating. Otherwise, the kiwi crop gets damaged. So the kiwi, to maintain that, electromagnetic drying or Mylar brand technology has to be used. So this is a kind of innovation we require. Apart from that, biomass-based bhattis or dryers are available it is indigenous, but it gives a lot of smoke, and smoke mixed with the cardamom. So what happens, the cardamom taste and its aroma get decreased, and ultimately the farmer doesn't get the price. So some sort of innovation with solar drying can be embedded. In Assam itself, we have more than 900 tea gardens. So tea drying is usually done with biomass. So ultimately it gives birth to CO2 emission. So solar drying can assist this type of things, but it should be turnkey project kind of thing, because all the tea gardens are having different capacity, and it cannot be directly replicated in linear regression. This dryer cannot be made like that. So a turnkey project has to be taken up. So this is also a kind of innovation we can think of. Wind, already I told you that we do not have much scope for wind power generation. In Arunachal Pradesh, there are a few pockets where we can get wind generation at 50 meter as well as 80 meter height. Particularly areas east side of Arunachal Pradesh, there is a place called Pasighat and Teju. Their wind speed is very high, more than 10 meter per second from early morning till evening. So that kind of wind turbines can be established there. But other places like Assam, some near to the riverine area, some scope is there. But Manipur, Nagaland, they have very less scope. Now this next renewable energy of interest is to utilize biomass. To use biomass directly by burning, give birth to carbon dioxide and particulate emission. So we can have a strategy for using biomass in different purposes. Like instead of going for a direct combustion of biomass, we can have a combination or co-generation of co-gasification or co-combustion of biomass with coal. Co-combustion is, of course, not a good idea because it will ultimately give greenhouse gas emission. So we can go for co-gasification of biomass with coal. But what proportion of biomass we use with coal, that matters a lot. Because the gasification technology, which is sub-stoichiometric air condition, in that condition, biomass and coal actually react together with alkali material of biomass. Alkali materials in biomass is usually potassium, aluminum kind of thing. But this potassium, aluminum, etc. of biomass at slightly elevated temperature react with silica that is present in coal, and they form K2SiO3, that is potassium silicate, or it is potassium aluminum silicate or calcium aluminum silicate. They act as a catalyst. So ultimately what happens, the carbon conversion is enhanced and the CO2 is converted to CO, which is less greenhouse effect product than CO2. So that is one of the factors why alkali material present in biomass enhances the efficiency of the whole system as a whole with reduction of greenhouse gas emission. Second important issue is that in the coal furnace or boilers, we require very high temperature for combusting the coal. But in case of gasification with biomass, the reaction occurs for gasification at very moderate temperature, around 450 to 600 degrees Celsius. So reduce the reaction at temperature. That is one of the advantages of biomass. Then it also reduces the activation energy, and it actually converts the char material that is present and tar that is formed due to the presence of biomass to gaseous product like producer gas. So that is the advantage of gasification of biomass with coal. So I'll just go for some of the setups. This is one of the setup we developed at IIT Guwahati, which produces 25 kilowatt electricity. These are some of the gas composition results, as you can see. So hydrogen is slightly elevated, but not high. Methane is slightly more, but CO is more and CO2 is reduced. And with a different equivalent ratio, you can see there is a drastic reduction of these gases. So regarding equivalent ratio of 0.8, usually it gives the optimal value of the gas production. The lower heating value decreases with different equivalent ratio, but we have fixed up equivalent ratio of 0.28 for this type of system. This gasifier is also an innovation, but it requires some of the decisions, like there is a here is a, in this diagram, here is a distributor plate. Designing of this distributor plate becomes very much essential. That can be a very good innovation. Apart from that, usually we require to have a proper solid circulation rate. That is very difficult to maintain. So that can be also one innovation. Then we tried with sawdust, bamboo dust, rice husk, which are locally available. There can be a numerous number of other things like pellets making of these biomasses. That can be also very thing. This pelletalizer itself is a one kind of innovation we can make. Pelletalizer that is available in market doesn't work efficiently. So a student who is working in this field can always go for this kind of innovation. Then another category is our biogas, which major constituent is methane and carbon dioxide. And these biogas applications has been also tested in our laboratory, and it is scrubbed so that carbon dioxide part is eliminated. So this is a scrubber having KOH solution. So designing of this with locally available material like kalakhar, what we call in Assamese, from bamboo, banana leaves, you can burn or you can char it. That have a lot of ample scope of having potassium and aluminum. So that is dissolvable in water. That actually can be one good solution for making this scrubber. Again, designing of this scrubber with different, it will be like a heat exchanger. Water filtration and all these things, pathway have to be found out. So this may be one good work. Then these are some of the applications of biogas. Even the cooking stove for biogas, designing of this is one kind of innovation, because it is not like LPG stove, whose flame velocity is different, and biogas is having low flame velocity, low calorific value. So designing of this dimension of the whole of the burner also matters a lot. So this can be one of the aspects. Then designing of the digester itself, we have some conventional digesters, but this digester is having certain capacity, like it can produce 3 meter cube a day biogas. But if we want 20 meter cube a day or 40 meter cube a day, scale up is important. So scaling up, simulation and modeling, this can be also good kind of innovation. This is one innovation we did in the year of 2006. It is a Samriddhi model where there is a 2 bathroom walls inside the digester. And this is 60 centimeter height from bottom. This is having a height of 70 centimeter. So what happens, there will be the flow pattern will be having some deformation, and residential time of these whole slurry will be long. In that case, the anaerobes get a lot of time to digest the slurry, and ultimately it gives better biogas production with the same capacity as this type of thing. So this is one of the model we developed. Similar kind of model can be also developed. This is status of hydropower. This is also kind of renewable, we can say. Ample scope is there to produce a lot of hydro, particularly mini and micro hydro has got the potentiality. This already I discussed. This is another unit with 50 kilowatt capacity made in IIT Guwahati, and we actually electrified this in one building in one of the places in IIT Guwahati for 7 hours duration. So here also there is a screw feeder. Designing of this screw feeder is very difficult because it actually has to take care of the biomass, that is like sawdust and rice husk. So because of the repose and goal of the screw feeder threads, it becomes stuck, the feed material stuck. So innovation is required in this aspect. So this another one is the distributor plate design also, that also plays an important role to increase the efficiency. Another one is the syngas that goes out from the system goes to a filter or series of filter. That filter has to absorb carbon dioxide, particulate, and tar particularly. So innovation is required in that aspect also. This is another plant I visited during my JSPS program in Japan. This is a Osaki power generation plant. In this plant, they have innovated, instead of having a circulating fluidized bed, they produce secondary flows inside the system. It is a 20-meter high, 20-meter long column, where the entire thing, some biomasses, 10% biomass they are using, and remaining are Australian coal. So ultimately, they are having a production capacity of 166 megawatt. You can see the outside view of this power plant. It is totally clean. No particulate emission is there. Efficiency has increased to 40% by this particular technology. And carbon dioxide capture has been found to be 90%. An advantage is that gas turbine operation in this power plant is at 1500 degrees Celsius. In India, we go around 1000 degrees Celsius. They have not improved the material of the gas turbine. Rather, they have made some impinging Z kind of thing inside the gas turbine blades so that cooling can be done at a boundary layer. So that is the achievement. And they are thinking to go for producing operate gas turbine at 1700 degrees Celsius by end of 2022. That will give 45% of efficiency to the plant. SOx emission is less than 8 ppm, NOx is less than 5 ppm, and particulate is less than 3 milligram per meter cube of the gas produced. This is another power plant with 10% coal mixing, again in Subu Electric Corporation of Nagoya in Japan. This power plant, as such, you can see it is clean, near to the sea, and they have produced a production capacity of 8.1 gigawatt with 5 units, with efficiency of 45%, 10% biomass is used. And the slash that is going out from the system is at such temperature, they form some glassy granules. These granules can be used as a topping in the road. So that has been already tried by them. Some of the other applications of biogas I am showing here, like power generation, then biogas genset, then this is a transport fuel in Sweden. This is in diesel engine dual fuel mode. It can be used. You can see the particulate emission has been reduced drastically with biogas. This is a PEM fuel cell or solid oxide fuel cell, where hydrogen and oxygen, they produce this electricity. They use ceramic catalyst at high temperature with nickel as anode. So directly, if it is a high temperature fuel cell, directly methane can be converted into the, instead of hydrogen, we can directly convert methane into hydrogen and carbon. So carbon, whatever carbon particles or fines come, they can be used for other purposes like making electrodes and other things. So I'll take just 1 or 2 minutes. Now, if we want to integrate all kind of renewables with conventional power plant, we require to have a building block like integrated operation and maintenance, AI and machine learning, digital twins and cloud and IoT. The expected solution domain is that consistency and safe operation at full load, partial load and transient load has to be done for the power plant, because when you have renewable, there are peaks, ups and downs of the power generated. So this influences the power plant again. So the power plant will be highly loaded. So again, in transient also similar thing happen. So we must have the 4 digital technologies so that we can reduce the overloading of the power plant at different loading conditions. Then optimization of the plant level and improvement in heat rate. These ultimately give rise to improvement in efficiency. Assets prediction and preventive maintenance, asset health diagnostic and failure prediction, then AR, VR, digital enablement and plant worker safety, artificial, augmented and virtual realities have to be adapted. So value addition to the client with the help of this digital technology can be reduction in CO2, SOx and NOx emission in the plant, reduction in operation and maintenance, then detection of fault and leakages, which is not possible by human beings so easily. So as much as 36 hours in advance, with more than 85% accuracy can be obtained with AI and machine learning. A huge financial saving is possible and plant life improves. So this is also one of the packages which have to be adopted now. So sustainability in the Northeast for energy supplies there is a large solar energy for solar PV and solar thermal application. Entire region has huge potential for mini and micro hydel plants. This needs to be exploited strategically. Then we have used biomass potential. This can be converted into high quality and clean fuel with appropriate technology like mixing of coal with biomass as gasification. Then cogeneration, that is already we discussed. Another energy generation technology can be integrated and made more reliable and sustainable by using high industrial revolution 4 technologies. Then above all enabling atmosphere has to be created with the help of policies of the government of Northeast and for adoption of new and clean energy. This slide, even though it is thank you, I am just hinting you out. These are the butterflies available in my place here, different type of butterflies. And this is the campus, newly grown campus in NIT Arunachal Pradesh. This is a particular dance done on the 15th August in our campus. It is a local dance. This is the pictorial view of our campus. And this is a particular flower, rose kind of flower available here. With this, I thank you, everybody. Thank you.
Thank you, sir. Thank you for your very nice deliberations. And with this, we are concluding here the sessions and conveying the thanks and gratitude to our keynote speaker, Professor Gautam Biswas. After his speech, he is also now also he is with us, and Professor Rajat Gupta, Professor Pinakeshwar Mohanty, and thanks to our session chair, Engineer Pradeep Chaturvedi, as a co-chair Dr. Raja Chakraborty, and our reporter Dr. Sagnik Pal and Dr. Deepak Chandra Das. So thanks to all. And now for our 7th session, technical session, we'll be meeting at, instead of 2:15, we'll be meeting at 2:30. So we'll be starting our session at 2:30 and we'll be completing at 3:15 or 3:45, and 4 o'clock our valedictory sessions. So with this, we conclude here. Thank you all.
Thank you.
Thank you.